to this short course on energetic materials. As you know, energy is something that we take as given. Electricity works all the time. Oil just flows. Anytime you go to the petrol station, you get what you want. But recent years showed us that nothing is really given. Petrol is not really automatic and it can be really pricey. Even electric energy needs some planning, and here we are. We will talk about the core of our energetic system that serves as a base for the whole energetic grid, not only the electricity, but also for the mobility. I hope you will have inspiring time, and you will learn something new useful for your future studies and future decisions. Have a great day.
And now it's my pleasure to welcome Professor Leichmann, who will give the first talk on uranium deposit in the Czech Republic. So good morning. I would like to say something about our research about all the data concerning uranium deposits, mainly Czech Republic. I will start with this diagram indicating temperatures, because the climate and energy is in last year very popular topic, and some people think that these two features are somehow connected. So if you look on this first diagram, on the x-axis you may see ages from 500 million ages to today. This is a time scala of the Earth evolution, and here on this axis you may see the average global temperature in Fahrenheit degree. And today temperatures are here. So we are in pretty cold climate, and the climate in the geological past was even 30 degrees Fahrenheit higher than today. So that means that all these statements like climate crises and irreversible changes or collapse of climate is nonsense. Climate not collapsed. Climate could get warmer or colder, nothing else. So and the variation here are quite large. This picture is very similar. Here you have a time axis in 1,000 years, starting around 10,000 years before present, ending here. And you have here temperatures in Celsius degrees, which were taken from ice core drilling in the Greenland. So it's covered Holocene. This increase of temperature is end of the last ice age, and you may see very strong variation in temperatures. In this last 10,000 years are at least 4 degrees Celsius. We are now here. Temperatures we are today, somewhere here, are much lower than in the past. And you may see here two very important maximum. This is Minoan warming and Roman warming. Or these peaks indicate climatic optimum and cooling following after the maximum cause fall of many important civilizations. This was a Minoan civilization, and here was a Roman civilization. So warming is positive, cooling is dangerous, and climate evolution. And the whole theory is here, in the end of 18th century, in the United Kingdom, start the burning of the coal, and the CO2 start to increase. And the main question is the today temperature increase here a result of CO2 concentration or coal burning, or this is just end of the little ice age? If you look this period, it is quite unusually cold period in Holocene. Usually the Holocene was much warmer and the cold period were much shorter. So, according to this geological record, it's completely not clear what is the real reason, CO2 or end of little ice age. And the question is why these temperatures are optimal. They are quite cold. Optimum were this temperature. So the increase in temperature on 2 or 3 degrees is nothing unusual in Holocene and will cause any huge damages in the Earth's history and so, in the Earth's civilization and so. And the people till the 18th century use just this energy. They used chlorophyll to change the sunshine to the corn, to the wood, and produce energy for food and to produce warmth and so. Actually, the today technology is the same. We use just silica to produce electricity from the sunshine. So both systems are relatively dangerous because the variation in sunshine, variation in temperature caused very strong, or could cause very strong variation in energy amount. Here, in the past, we saw the results, fall of Roman Empire, fall of Minoan Empire, and so. And it's really not a good idea to produce all energy just by sun. The production of the fossil energy will end quite soon. So the today accessible fossil energy reserves will be consumed in 50 to 100 years. For instance, China declared that they will stop the fossil energy 2060. That's clear because the all coal reserve will be exhausted. So England stopped it because the main reserves in England are mined out. So after the 100 years, after the whole fossil energy will take, say, 400 years, not more. Solar and nuclear energy remain. And the main enemy of the solar energy are large volcanic eruptions. If we will produce whole energy using solar panel or wind turbine, such huge eruption will completely destroy the supply chain. So in the past there are 3 major eruptions known which could cause such troubles. The biggest one was the eruption 536. It's not known which volcano it was. It's probably a combination of several eruptions. One was possibly Krakatoa, and the second one was unknown volcano in Iceland. and because it affected East Roman Empire, it was a this eruption is very well known, and it's described the sun rise weak and they appear bluish. At noon, no shadows from people were visible on the ground, and so the temperature goes down up to 2.5 degrees Celsius. This eruption of Tamboran Krakatoa were certainly not so strong. However, they influence the climate as well, and certainly such huge eruption will strongly decrease the production of solar and wind energy. Nuclear energy is independent on natural forces. However, uranium has a very specific behavior on the market, and this is very different from other materials, other metals, and the economy, therefore, is very difficult to predict and calculate. So the mining and extraction of uranium is complicated not by nature, it's complicated by society itself. So this is the history of uranium production in the last 70, 80 years. The main period starts here in 1945 with the first nuclear bomb. It was a short period somewhere here in the 20s and 30s, but it was a period connected with uranium mining, but the reason for mining was not uranium, but it was radium. I will talk about later. And you have years and year production of ton uranium each year. And you may see the strong increase in the production from 40s to 60s here, and the peak somewhere around 45,000 tons of uranium. All this was used to produce the nuclear weapons. Everything what is here above this line is a military production. What is below this line is a production for nuclear reactors. So this production for nuclear reactors starts significantly around 70s and to reach the maximum somewhere here, the maximum production of uranium around 65,000 tons. And what is interesting is this gap. So this is a requirement of uranium, and this is a production of uranium. So, and we have here, so big hole, starting 1990s, and it takes 25 years. So the reason is that part of the military production of strongly enriched uranium was used to the reactors. And this is the main reason, main economical reason. This is because it was a Chernobyl event here, and 1990s is the fall of Eastern Bloc and the beginning of the reduction of nuclear weapons from United States and mainly Russia, and all countries deliver lots of uranium to the market, and they completely destroyed the prices. And on this picture you can see the production of individual countries. If you look on the year 1960s here, the majority of production is Canada, United States, Southern Africa. More than 2/3 or more than two-thirds of production of uranium production was produced in the so-called Western countries. Czech Republic is here, very important production, approximately 5 up to 10% of world production this year was produced in Bohemian Massif. Eastern Germany is more significant. The deposits in Eastern Germany, in Saxony, in Erzgebirge, was quite high. And you may see the huge production of former Soviet Union, which is probably today Kazakhstan. And today I will show you on the better picture. So the main reason for uncertainty in uranium prices and so is this double use for reactors and for nuclear weapons production. So there are the uranium prices, which are in dollars per pound. Before the 70s, the price of uranium was unimportant. Everything was mined for military purposes, and the price was unimportant. Doesn't play any role. And starting the production for nuclear reactors bring the uranium to the market. And you may see here the very low prices in the 90s. It is below 25 dollars per pound. So it means it was cheaper than good beef. 1 kilogram of nice piece of beef was cheaper than uranium. Was more expensive than uranium. Uranium was cheaper. We have one peak here, and here we have it was connected with the oil crisis. Usually, when the oil starts to grow, uranium follows it. And we have here another depression, and just in this point, the mining of uranium was stopped in Czech Republic. And after the stopping, the price started to grow. So they selected a really bad time, but the last uranium mine was closed 2070. And now the price is around 50 and continues to growing. So how is it with the uranium production today? Almost 50% is produced in Kazakhstan. Very cheap mining because they use it subsurface leaching. They just pump sulfur acid, which leach out the uranium and pump it. And this is in desert, very cheap production. Similar is Uzbekistan. Namibia, Australia, Canada, around 10%. China, 3.9%. However, the so-called Western countries, it's mean Europe and United States, produce less than 90% of world production. However, they consume 2/3 of the whole production. So EU, European Union, and United States are very vulnerable by uranium market. Czech Republic produces in the year 1960 to 1980 approximately 3,000 tons uranium of each year. It was a quite high production. Today it is 8%. It will be 8% of the production. And today the world produces less than 50,000 tons of uranium dioxide. Resources are quite different if compared with produced. The major reserve is Australia, 28%. Kazakhstan, Russia, Canada. And all other countries, Namibia, Southern Africa, has a much lower reserve. United States just 1%, Mongolia 2%. Czech Republic is not listed here. However, if we look on this table, it shows slightly different view. There are this reserve, total reserve, in the, with the price $130 per kilogram. And the total reserve are more than 6 million tons. Czech Republic has that, almost nothing. However, if the price grows to the $260 per kilogram, the reserve of Czech Republic are quite high, more than 100,000 kilograms, 100,000 tons. So it shifts in the reserve to Czech Republic to the certain place in the world. So the Czech uranium mining strongly depends on the price. Today price is similar to this level. So the economy seems to be bad. However, the increase of the price of uranium on the world market could certainly bring the Czech uranium back to the market and could make the economy reasonable. However, the main danger is here. There is military reserve. Usually, this is a strongly enriched uranium up to 100% of uranium-235. However, Russia and the United States own a very huge amount of uranium, which is equal to 585,000 tons of natural uranium. It means 12 years of today world production. So this reserve will cover the consumption of uranium from the whole world for 12 years, at least 12 years. So it's somehow strange because uranium miner must hope that no other reduction of nuclear weapons happen and so, because otherwise this will be completely destroy the market for 20 years, certainly, of uranium. However, today's situation seems that certainly China will increase the amount of nuclear weapons, and Russia and the United States seem to be not reduce it. So this reserve probably stay in this highly enriched state and will be not end on the market because the market will be destroyed by this. And this is the situation with reserve and prices. These light blue boxes are uranium reserve with the price $40 per kilogram, quite low. And they are getting lower. So this is just less than 1 million ton. So the really good uranium deposits are mined out. They are not so common. Slightly better is this with prices around $80 per kilogram. The total reserve are more than 2 million tons, and the main reserve of uranium are available by the prices of $130 per kilogram. This is this 4 and 5 million tons of uranium, and this reserve, the worst reserve, which could be mined and very high expenses. As expenses are 2 million tons are increasing. They doesn't exist here. So and together all this today known reserve are 8 million tons with very the reserves are connected with the high uranium prices. And Czech Republic stopped the mining somewhere here is the lowest prices. So the price on the market was less than $40 per kilogram, and today are much higher, around 130. So probably some deposits could be mined in Bohemian Massif. So this is a consumption or uranium requirements for energetical use. The main consumption is North America, Canada and United States, European Union, Europe, non-EU is mainly Russia, East Asia, China. This is interesting here because EU produces nothing. This is no mining on uranium in Europe. However, EU states consume more than a quarter of the world production. This picture compare the production and requirements. So, United States, for instance, they need approximately 2,000 tons of uranium and produced almost nothing. Japan, France, even France has a very high consumption but no production. Russia and some countries like Canada, Australia, Kazakhstan, Namibia, Uzbekistan produces lots of uranium. However, the consumption is nearly zero. So this is a strong disbalance between mining and consumption. Czech Republic consumes about 1,000 tons of uranium annually each year, and which is in the price, if the price is 130 US dollar per kilogram, the price of the uranium is 2 billion Czech crowns. So this is probably not economical today, but with the higher prices, 260 is the top price. The value of the consumption is 5 billion crown, and it could be possibly economical. It seems to be that the amount of nuclear reactor is growing, and therefore the production of uranium must grow as well. There are data from the last year. 53 nuclear reactors are under construction. 90 are planned, and 300 are proposed. So today, 430 or 440 reactors is operation. So the amount of reactor seems to be, or will be probably increased, and therefore the production of uranium must follow it. It's necessary to say uranium or thorium because some countries, for instance India, they will cover or they will use thorium instead of uranium as a nuclear fuel. So enriched uranium, you need approximately 7 tons of uranium. So just in Yakimov, which is pretty small deposit, it was 8,000 ton uranium were mined there. From this amount, 1,200 Hiroshima bomb could be produced just from one mine. And the whole Czech production, which is a little bit more than 100,000 tons, will give more than 40,000 uranium bombs. So only the Czech mining of uranium, or all the Czech, or the uranium which was mined in Czech Republic could completely destroy the whole world. So the energy here in the uranium is high, quite high. And whole the Czech production to the 60s, 70s was used to produce the nuclear weapons. The usage of uranium started in the 19th century as a coloration of glasses. Sometimes on the old castle you may see such green glasses and so. So they use it to color glass. They use the uranium to color ceramics and so. So the tradition, or the mining in Jáchymov, has a long tradition, and the uranium is known there for a long time. So in the 20s, it was several tens of tons of uranium were mined, but not because of uranium, because of radium. And radium was discovered as well in Jáchymov because Marie Curie discovered that the metallic uranium is less radioactive as uranium. So it means that in the uranium ore must be another element which is more radioactive than uranium itself. It was a radium. So radium was discovered in uranium, and to produce 1 gram of radium, they need 8 tons of uranium. And in this time, 20s, 30s, radium and radioactivity generally was considered as very healthy. They produced some ceramic water dispenser which was enriched on radium. They produced some medicals which were based on radium. However, 1932, it was clear that too much radiation could cause some healthy troubles, and radioactivity was considered as a danger from this year. However, in the 20s, 30s, radioactivity was healthy. So, and the Czech Jáchymov was used first by Germans. Germans tried to create a nuclear reactor during the World War II, and they used uranium from Jáchymov. However, they were not. The experiments were not successful, and the mining started immediately with uranium immediately after the end of World War II, and increased very rapidly in 10 years from 0 to 3,000 tons. It was mainly Jáchymov and partly Příbram. What is red here is a production in mechanical separate minerals from rich vein deposits. They will be able to separate it mechanically, and here this green stuff is separation, is a chemical leaching or chemical separation of uranium. And the production fluctuated between 3,000 tons, which was in 60s, and it decreased to 2,000 tons in the 80s, and from the 80s and after the Velvet Revolution goes down up to 500 tons, and in remain on this level to 2017. So the production was quite high. Here, just at the beginning, was the production very important because they were on the world where just three known, or three localities where uranium was mined, and just one, Yakimov, was under control of Russians. Other occurrences were controlled by Britain or by United States. Therefore, the production here was crucial for the starting of the nuclear weapons production in Russia. There are two types of uranium deposits in Czech Republic, vein type and sandstone hosted. Vein type produces more than 70%, and uranium and sandstone hosted just around 27-28%. Majority from these uraniferous sandstones are mined in the Cretaceous sediments, Permian or Tertiary, are just limited. There is a map of uranium deposits which were discovered in Czech Republic. The biggest one is Příbram. The second biggest is Rožná, and there are several deposits hosted in the sandstone in the northern Bohemia. Jakimov is here, and you may see lots of small deposits, which are usually located in the Modern zone, Saxo-Thuringian zone, and Cretaceous sediments. Some small are, for instance, in the Jeseníky Mountains, and in Moravian zone, Brno-Istulian zone, there are no deposits. There is another map showing the similar situation. The blue stuff are deposits which are mined out, and the red are deposits with some reserve. You may see here once again the biggest Czech uranium deposits with the highest production was Příbram, 38%, Rožná 18, Hammer 11, Stráž 15, and then some other small, Jáchymov 6, Horní Slavkov, Western Bohemia, and so. The most important was Příbram. However, the biggest reserve are today here in the sandstone. So this picture indicates reserves. They were quite high. This blue, yellow are total reserves, and this, say, red are reserves in the better category, in high category, which could be easily mined. And the highest reserve was in the 80s, in the beginning, 1980, under 20,000 tons, and it decreases slowly, and after the Velvet Revolution goes down very, very rapidly. This is certainly not mining. The Czech Republic doesn't mine 50,000 tons of uranium. This is just administrative done. This reserve were, so say, killed administratively. They were not mined out. So there are reserves today for production. Now the production is 26 ton, and 20 years ago was, or 30 years ago, was 1,000 times higher. However, the reserves which could be mined are quite low. However, total reserve are quite high. So the increase of price of uranium will probably shift this uneconomical reserve to the economical one. And this, which are not economical, will be shifted to this. These are based, I don't know, on the price is $40 per kilogram. An increase of the price will probably shift the reserve in the area which could be economically interesting. So, and this is my favorite diagram, which indicate that the Czech Republic has a much higher reserve than we think today. This so-called learning curve for unconformity-related deposits in the Athabasca, but it could be applied on any uranium deposit or any raw material deposits generally. So, you may see here 3 stages. One around 60s, 80s, and in the future. In the 60s, there was a quite cheap exploration expenditures. They used just prospection driven methods. So it means spectrometry, gamma spectrometry, X-ray spectrometry, and so on. They used aircraft-based or ground measurements, and so they rules are very simple because uranium is radioactive. They walked just with spectrometers around the field and found anomaly, start to drill and start opening mining. Very cheap and simple methods. Model-driven exploration is much more expensive. However, they discovered much more deposits, and the best deposits like Cedar Lake and McArthur River was discovered by this exploration, by this model-driven exploration. It means that the geologists studied these deposits which were discovered during the first period, and they learned something about genetic relation, age, enrichment mechanism, and genetic relation, and so, and apply it on the other part of countries, and they found these huge deposits. These are very excellent deposits with a uranium concentration up to 10%. Usually the Czech deposits at 0.1%, up to 1%. So, and Czech Republic stopped the exploration just in this first stage. In Czech Republic was used just spectrometry and drilling to found deposits, and no genetic models were prepared or calculated to see this, to be in this field. So the application of new methods like secondary dispersion aureolas, dating, fluid inclusion study, microchemistry, and so could probably help to discover new deposits in Czech Republic. And we got in the last 4 years a project dealing with uranium, and we tried to prepare a model, genetic model of the deposits which are related to the Western Moravia and the vicinity of Rožná mine and so. And we try to find some critical parameters which could be important to discover new deposits. Actually, you will need 3 basic conditions to form uranium deposits, mainly the main deposits. First of all, you need a primary source of uranium. So rocks with an increased concentration of uranium at least up to 10 ppm. After that, you will need fluids, which were able to extract uranium from the primary sources. These fluids are usually oxidative nature, and now pathways for fluid migration. And third condition is a reducing environment. So environment which could reduce the fluids and deposit the uranium ore. So this is the concentration of uranium in the different rocks. Average in the upper crust, average concentration is 2.7 ppm part per million. It means 2.7 gram in ton. And some rocks has a nicely increased amount for instance, granitic rocks, nephelinic cyanides, and so. So these rocks are or heap shales, black shales, which could be paramento rocks for uranium deposits. I will talk about the Rožná deposit, which is say 40 kilometers northeast, northwest from Brno. The deposit itself are mineralized zones, which are actually brittle faults, which are filled by carbonates, graphite, and uranium minerals. The mineralization starts at the surface and could be followed up to 200 meters. This deposit is slightly similar to the Valhalla deposit in Australia. You may see here the similar structure, a variegated series with paragnesis, amphibolite, some marbles. The same is here, metasediments, amphibolites, and mineralized zone. However, this deposit is much older. Rožná deposit is 270 million. This is 1.5 billion by billion. It's much higher temperature. Rožná is so 150, 170 degrees. This temperature of origin of the deposits are quite higher, but the fluids were probably the same. However, this is a typical for all uranium deposits. Origin of fluids is questionable. It's usually not clear. You can identify source rock, you can identify reducing environment, but the fluids remains enigmatic sometimes. Valhalla and Rožná have a similar ore structure. This is Valhalla, uraninite replacing pyrite. This gray stuff is pyrite, and it's replaced by uranium. And very similar feature you may see in Rožná. Instead of uraninite, we have a coffinite replacing pyrite. Mineralogy is very similar on this diagram. Zirconium, silica, coffinite. You may see that Valhalla is a mixture between uraniferous zircon and coffinite, and the same in Rožná, coffinite and uraniferous zircon. And source rock for these deposits, Valhalla is somewhere here, and there are lots of deposits in the vicinity, and the probable source of uranium is this granite, which is locally called Kitty Plain microgranite, which is the probable source of uranium. You may see in this Pluton some shear zones which are depleted in uranium. These rocks are nicely visible. They are enriched in uranium and thorium. Microgranites, 12 ppm uranium, 54 thorium, high potassium. And we compare it with so-called Čech massive in Mononubian zone, which has an even higher concentration, 4 to 25 uranium, up to 60 thorium, up to 6 potassium. And one small facies, one small body, has a really anomalous uranium concentration, 370, more than 1,000 ppm thorium. So we have a probably the granitic body. There's an elevated concentration of uranium for both deposits, for Valhalla, Kitty Plain, and for Rožná, Turbachite. And even we have a similar features in this rock. This is a X-ray fluorescence mapping from the Kitty Plain microgranite. And you may see here zircon and thorium zirconium silicate. And in this red and yellow colors, mobilized uranium veins. The same here, thorium zirconium silicate, and mobilized around uranium boundaries. So here, there is a visible migration of uranium. So uranium was mobile and was able to migrate from the parental rocks to the vicinity. The situation with the Czech uranium deposits is so. We have here structure, some faults on which the deposits are related, are placed. Slavkovice, Petrovice, Nová Ves, Rožná, Rozcochy, Milasín, Bukov, Habří, Olší. Around this line, we have these deposits. And this is the so-called Třebíč-Puton. This is the granitic body with an elevated uranium concentration. And the whole is a part of the whole Variscan belt, starting somewhere in Portugal, in France, going to the France, Schwarzwald, Bosch, and to the Bohemian Massif. So here in the France, they are in the same zone. Uranium deposits located as well, which are probably of similar origin. This is one small profile to the Rožná deposits. We use a gravity mapping to identify the whole zone. So you may see here, this is the zone which is detected by gravity, and on these zones are located uranium deposits, this is red, and some fluoride deposits. And another zone runs here, and along this zone are located deposits which were mined, Jasenice, Tasov, and Brzkov. So we have here probably two tectonic lines. Along these lines, the fluids could migrate, bring fluids, and so this is a gravity map. We indicate the fault here is indicated by gravity minimum because of cracking of rocks and so. And on these zones are related these deposits. This fault continues to the Carpathian Foredeep, and that is known as a Vranovice structure. And if it's really true, this is a really energetical fault, because here on the surface, some uranium deposits are connected with this fault, and in the subsurface, in the Vranovice graben, this is this fault. This is a profile. Some oil is located. So this could be very important fault. And we tried to analyze the ores, and we found very interesting things which are connected with the uranium ore from this Rožná listing. Usually, they are enriched on zirconium, niobium, yttrium, rare earths. So here you may see the backscattered electron image, nothing unusual. Distribution of uranium, normal along this zone, is a little bit higher. However, the uraninite is on the rim replaced by coffinite, this energy silica, and for instance, zirconium and niobium. Niobium is distributed along these faults, along these cracks in the mineral. So this is a typical feature for these deposits is the enrichment on other elements which could be used. However, these elements were not mined in the time where the mine was in operation. So, I will show it here. We have two different kinds of ores in the area. The first one, are typically uraninite with a high uranium content and low silica content. There are mines Rožná, Olší, and Slavkovice. And another type, which is enriched on silica and depleted in uranium, which is Rozcochy or Rožná Jasan. In the center part of the whole structure are these ores, which are slightly depleted in uranium, however, enriched on yttrium, niobium, zirconium, and so on. We provide a chemical dating, and this kind of ores, depleted in silica, they give very nice AGs, 278 typical Permian AGs, Slavkovice, Olší, and this group, which is slightly enriched on silica and other metals, seems to be a little bit younger, 250, 237, which indicate that this enrichment on silica on other elements is secondary feature. So the primary ore was later affected by migration of another fluids, which were enriched mainly on silica, but what is more interesting, on zirconium, niobium, and other elements. Together with a colleague from France, we use a much more precise style of dating, using SIMS analysis, and we got very similar AGs, 270 plus minus 7. It means that the whole deposits in the area are Permian. And this is a complex diagram indicated fission track dating. I will try to explain it briefly. Here we have a time, 280 and today, and here we have a temperature. And the dating of apatite would be dated by a method called fission track, and this data could be interpreted in this way. We have a 280, 270, so this is the time of origin of the deposit. Very rapid uplift and cooling of the rock. They cool down from 270 to 60 in less than 10 million years. And later, they cool down very slowly, almost very slowly. So it means that this is a rapid uplift which could be connected with the fluid flow and very rapid erosion. So therefore we think that the fluids could be Permian fluids connected with eroded basin which were similar to, for instance, Boskovice, Foro, and so on. They produce fluids to uranium migration. Uranium was leached out from the Grubach, and during this interval, the deposits originated or were created. This very similar feature, typical for a broader area. Rožná mine is here, and we try to date it another rocks in the vicinity, and we will see the same feature. Very rapid Permian uplift. And this is a distribution of the fission track AGs. In this area, we have this is badly visible. This is a Třebíč, Pluton is somewhere here, Rožná is here, Brno is somewhere here, here is a Jihlava. and this area we have a Permian ages, Permian uplift. So we suppose that the uranium deposits originated in this area. This uplift was much later. This is Cretaceous uplift, and probably it is not too much sense to search for deposits in this area. It's better to explore this area with these Permian ages. And now a few words to the parental rock, to the Drábová. It is dark rock, it's potassium feldspar, some mafic inclusion rich in biotite, with some amphiboles, some geochemical parameters which are not important now. And this is a map created by Dr. Gnojek. This is a radioactivity map of the eastern part of Bohemian Massif. We have here Brno, Přibyslav, Havlíčkův Brod, and there are these uranium deposits. And this is the so-called Třebíč Pluton, Třebíč Massif, with another Jihlava Massif here and some small relics here. And you may see the very high uranium contents, up to 20-25 ppm in the Drábová. All other rocks are either depleted in uranium, Moravian zone is depleted, and what is interesting, this is a Boskovice Furrow, Permian Basin, which is enriched on uranium. So this is another indication that these fluids connected with the formation of the basin could be somehow related to these deposits. Certainly, we have here very nice granitic body, which is originally primary enriched on uranium. The body was probably much bigger. We try to estimate the formal extent. Yeah, you may see it here. This is the formal extent of the Pluton. This is now just erosional relics. So the original intrusion was around 1,000 square kilometers. Today extension is less than 500. The maximum thickness was probably around 2 kilometers. And we calculate the formal content of uranium in the whole body, 28 million tons. So this is a quite high amount, and this is certainly source rock, as a high probably source rock of the uranium metal. So in the Rožná mine, just 20,000 tons was mined. So the uranium must be hidden somewhere here in this area. It's certainly nonsense to mine this Pluton because the concentration 40 ppm is too low. The minimum contents for economical mining is 1,000 ppm. 10,000 ppm, 1% will be okay. Most favorite area to find new deposits is the area of Brzkov. In Brzkov itself was a former mine, and you may see here concentration from drill hole. Drill holes with concentrated uranium contents up to 600 ppm. There are lots of this orange stuff is around 70 ppm. And we have here this Drábová, Třebíč Pluton, and two tectonic lines. On these lines, Tasov and Jasenice are located. On this Přibyslav zone, there are no uranium deposits known there. However, here in the crossing of these lines, the concentration is quite high. So the reserve calculated for Brzkov are 3,000 tons. We speculate it must be much bigger. So we hope, or we speculate, this is a just idea here, must be below the surface much bigger deposits than 3,000 tons. 3,000 tons is nothing. This is consumption for 1 year, but probably this structure indicated much bigger deposits could be there. And we look for the uraniferous mineral in the Durbachites. We found many of them. Apatite has no uranium. Zircon has some uranium, but lots of inclusion of uranotorite, and so we have a torite with thorium content around 60 and elevated uranium content of 10%. We have a uraninite, monazite with elevated uranium content, titanite with several tens of ppm, allanite and strongly altered allanite. So we have lots of minerals with a high or elevated uranium content. And what is important, we have a secondary minerals indicated mobility of uranium. Here there are some cracks which are filled by zirconium, thorium silicates. We have some rare earth carbonates around thorite. We have a secondary titanite enriched in uranium, in biotite, monazite, allanite completely replaced by monazite and rare earth carbonates. And so this is another type. And what is more important, we have evidence for strong mobility of uranium. Actually, we are proud because we have a much better picture than the colleagues from Australia, done by our colleagues on MicroPro or our colleagues by laser ablation. You may see here amphibole with a zircon inclusion. And you may see here distribution of zirconium, uranium, cerium, yttrium, and thorium. Even very unmobile elements like zirconium is mobile. So it fill the cracks around zirconium. The same uranium, quite a nice mobile, cerium. Why is it so? The reason is high uranium content in zircon. Zircon becomes metamic. So the structure is destroyed by alpha particles. And usually the specific gravity of zircon is 4.6. After metamictization, the specific gravity decreased to 4. It means that the volume increases. And the increase the volume completely cracks the rock around, because the amphibole is very solid phase, and the increase of volume of the inclusion completely cracks and open the cracks in the surrounding minerals. So, and the cracks were used for migration of this mineral. So we have a nice evidence for uranium migration from the uranium-rich mineral in this pluton. So there are lots of examples. This zircon is completely destroyed by metamictization, and you may see here the zircon itself is free of uranium, and all uranium is around the zircon, so migrated out from the crystal. So there is a very nice evidence for uranium mobility and even for the mobility of yttrium, zirconium, which are enriched in the ores. So we have a geochemical evidence, structural evidence for strong migration of the same element which form the uranium deposits in the vicinity. Moreover, the Třebíč pluton has the same exhumation history, rapid uplift, cooling, apatite. They have the same age as the uranium deposits. And what is very important is that we have some zones which are depleted in uranium. For instance, here. So this red stuff indicates zone in the whole Třebíč pluton, which are relatively depleted in uranium. So we have evidence in the local scale and in the regional scale for large-scale mobility of uranium. And the uranium deposits are somewhere here. The pluton was high probably above, so located above the above the deposits. So highly probably these deposits are connected with this pluton, and in this area, this is the most favored area to search for new uranium deposits. Some geological conclusion, and the main conclusion of my lecture is Czech uranium deposits are not exhausted, they are just undiscovered. So there is a good chance to find new uranium deposits, not only in the Sorozhna area. The same is valid for Příbram, Jáchymov, and other deposits. And highly probably the highest potential have the Cretaceous sediment in northern Bohemia. In this area, really huge deposits, raw front and sandstone hosted could probably exist. But problem is their mining. It's a low concentration, and leaching with the sulfur acid was successful, but very dangerous for nature in this time. So we hope that the perspective of Bohemian Massif in the uranium ore are great. However, you may see the prices of the discovery. They were $1 billion. So Czech Republic is slightly cheaper than Canada. However, $1 billion are necessary to really explore or examine this theory and try to find these deposits. So thank you for your attention. And if you have questions,
let me welcome Dr. Dana Drábová from the State Bureau of the Nuclear Safety, to be precise, who will give a lecture on nuclear energy and the Czech Republic past, present, future. Welcome.
So good morning, everybody. It's my pleasure to be here to share with you some thoughts and ideas and information concerning nuclear energy and the possibilities it has for serving to our growing energy needs. My talk has the title Nuclear Energy and the Czech Republic, past, present and future, but it won't be mainly concentrated on the Czech Republic itself, because I think that we need for the good understanding of the situation in Czech Republic, broader context, and even much broader can be covered by several decades, maybe, of the development of peaceful uses of nuclear energy. So we will start with some general information about the energy and its role in mankind's life and prosperity, because it's clear that modern energy created our prosperity. It means that we can say that social-economic development depends on the availability of lighting, heating, motive power, mechanical power, transport, telecommunication. We also speak more and more about sustainability and sustainable development. This is closely connected with the access to clean water, agriculture and industrial productivity, healthcare, education, job creation, and also, and this is more and more spoken about, climate change mitigation. If you look on the countries like ours, we see that energy has been a relatively low profile issue for some years, several decades. After all, there were no major power cuts or disruption to energy supplies during the last quarter of 20th century and first quarter of the century 21st. How closely is availability of energy connected with the quality of life of people? We can see from this picture, showing the relation between energy consumption per capita annually in gigajoules and an indicator that is called the Human Development Index. The Human Development Index is a composite indicator consisting of, for instance, expected life expectancy, child mortality, availability of vaccination, access to healthcare, access to education, and other sub-indicators. What we can see from the picture, I will try, excuse me, to find the pointer. Okay, it works. What we can see that there is a really strong correlation of availability or access to energy and Human Development Index. The higher the value of Human Development Index, the better the quality of life in individual countries. So you can see that up to some 100 gigajoules per year, there is really strong correlation between the quality of life represented by Human Development Index and access to energy. We can see in this part of the curve that there is quite a few countries, some of them densely populated like Pakistan or the most populated country today is in the world, India, with quite a low access to energy. We can see here that quite a few countries, especially in Southeastern Asia and Africa especially, those are countries with access to energy on the level of 20 to 50 gigajoules per year per capita. That means on the level of first agricultural civilizations some 10,000 years ago. What can we see from this picture as well is that somewhere around 120, something like that, gigajoules per year, there is a saturation of the curve. The meaning of it is that another increase of energy consumption does not contribute that much to the quality of life. You can ask where the Czech Republic is in this picture. Somewhere in the place of Japan or Germany. That means our annual energy consumption is around 100 80, 190 gigajoules per year per capita. And with this, we are already in the part of the curve where there is really a good reason for rethinking what is our say way of life what concerns the consumption of energy. And we are already in the part of the curve where the energy consumption really should be an issue what concerns the possibilities how to limit it or decrease it at least a little bit without substantial influence on our quality of life. And then you can see countries with extremely high energy consumption, where really the relationship with the quality of life is not possible to detect anymore. You have here the Middle East oil mining countries, but you have here also United States. So from this relatively simple picture, we can see quite a substantial amount of information what concerns the role of energy in our life. Now I would like to show you last 200 years what concerns the ways, the sources mankind covered their energy needs. And what can we see from this picture? Even in the half of 19th century, the overall annual energy consumption was very low comparing to nowadays amount. And we can also see that almost all of primary energy sources available to mankind were some kind of biomass and also the strength of animals and so on. So from the point of view of today's approach, at least of some groups, it was very green, very ecological, but not really. Because, for instance, in Great Britain, United Kingdom, the use of wood led to substantial deforestation, and also it was a driver to use coal as a replacement for wood, and it was also a driver for the Industrial Revolution. That means for development, inventions, innovations like steam engine, which allowed two things: to mine coal from deeper layers, and on the other hand, to let the steam work and to replace very, very hard work of people in manufacture. If we look further on the picture, we can see that Industrial Revolution started very dynamic use of fossil fuels. In the beginning, coal. Then we can see a growing part of for oil. Interesting enough is that oil started to play a very important role of the #1 primary energy source only after the Second World War. And of course, together with oil, we can see growing use of natural gas. With the more and more use of electricity, we can see also the most important renewable source in our energy mix. Even today, that means water. Water power stations, and from say 50s of 20th century, we can see a role or share of nuclear power, which will be the main topic of our today's discussion. For nuclear energy, and I do apologize now because there will be some slight overlap, maybe with what was already told or shared with you by my predecessor, because I will touch on uranium from, I would say, the very beginning of our planet, and I will touch some milestones in the history of uranium, because of the uranium is chemical element enabling to use nuclear energy. That means the forces that keep atomic nuclei together in our energy mix. First of all, one information that may be a little bit surprising. That means that the radioactivity in the Earth mantle, that means especially radioactivity of uranium, thorium, but also other radioisotopes, is responsible for approximately a half of what we call geothermal energy, because the radioactive decay of elements I have just mentioned and the production of daughter isotopes release heat energy, and as I have mentioned, approximately a half of geothermal energy is produced by radioactive decay. Here we can see, fortunately enough, a slow decrease of the amount of heat produced in the Earth mantle. And we can also see here that this slow decrease is also due to very long half-life of uranium-238 and also thorium-232. We can see here radioactive decrease or radioactive decay of uranium, and also radioactive decay of thorium. Both these elements have a very long half-life. By chance, uranium-238 has a half-life approximately the same as the time when our planet originated in our planetary system. The presence of uranium in Earth mantle also led to first nuclear reactors working on the principle of nuclear fission. Some 1 billion years ago, there were so-called natural reactors where the chain fission reaction was present. We can see here one specific locality in Gabon, in Oklo, Africa. There is still very good uranium mine in operation, the surface uranium mine, and it was proven by a series of radiochemical and other analyses that in this locality, as I have mentioned, 1 billion years ago, approximately, the first discovered natural reactor worked. Of course, the time without any interaction with our predecessor, because it was very, very long ago. So man didn't invent fission reaction or nuclear reactors. It's something our Mother Nature invented by itself or herself, and we also step by step learned how it works and learned how to use those strongest forces in our universe. Let me now move to closer historical period what concerns uranium. Uranium was discovered in 1789 by Saxonian chemist Martin Heinrich Klaproth. It was not in Yakimov or Joachimsthal uranium, but it was in uranium ore also on the territory owned by Schlicks, but from today's geopolitics on the other side of the border in Saxonia. Uranium was named after the planet Uranus, discovered shortly before, and this chemical element was, say, interesting, but not of much use, because it was just mentioned some minutes ago that it was the uranium ore from Joachimsthal was called pechblende or pitchblende because it was a bad luck to come to the deposits of Joachimsthal uranium ore uraninate. It was just clear that there will be no silver anymore. Maybe there was a second reason to call it backblend or Smolinets, because miners staying for a long time in this purely vented mines sometimes were ill, and were ill with a bit strange for that time to describe illness, and now, according to say diaries of Mathesius, working in Joachimsthal as a teacher and also pharmacist, we know that this strange illness most probably was lung cancer caused by inhalation of radon and its daughter products. And in the picture, you also see what was already mentioned. That means that uranium ore, to be more precise, was mainly used in glassworks to color very nicely, very, I would say, rare pieces of glasswork, and we use now or glass making factories use now depleted uranium to color and to get this very, I would say, nice and bit, how to say it, exclusive color, because it's sharply yellow-green color that is not easily replaced by the compound other than uranium ore or uranium metal. Step aside for a while, because I would like to mention that in the end of 19th century, we began our journey to, I would say, nuclear age. And in the very, very beginning, it has nothing to do with uranium. But this was only a very beginning, we will see. Everything started with the discovery of Wilhelm Conrad Röntgen and his famous X-rays. X-rays paved the way for the interest of scientists in strong forces, and paved the way for the interest in nuclear sciences. And by the way, X-rays or Röntgen rays are nowadays and will be in the foreseeable future the basis for most frequently use of nuclear technology in our lives, because in the medical area there are more than 4 billion of X-ray images made annually in the world, and it's indispensable for medical diagnostic. Now we will come back to uranium. Because discovery of natural radioactivity by French scientist Antoine-Henri Becquerel was based on the observation of luminescence of uranium salts. And during these experiments, Antoine-Henri Becquerel discovered that there is not only visible light emitted by uranium salts, but there is something invisible but very strong that can cause darkening or blackening of photographic plate without even direct contact. And after several weeks of intensive thinking, Antoine-Henri Becquerel discovered this new compound of the radiation emitted by uranium salt as a feature called radioactivity. It was mentioned that very important discoveries are connected with Marie and Pierre Curie's, that means discovery of two new chemical elements, polonium and radium, and Marie Curie obtained 2 Nobel Prizes for these discoveries. The first one with Pierre Curie, who died soon after by disaster, and the second one already alone. I tried to find out how many double Nobel Prize winners are there in the history of the prize. Not so many, around 10. And the second thing is that Marie Curie was the first woman to obtain Nobel Prize. As maybe it's worth mentioning, Wilhelm Conrad Röntgen was the first Nobel Prize winner for physics in 1901. Yeah, maybe I will mention this picture because Marie Curie Skłodowska visited, was invited to visit Czechoslovakia. She was invited to visit it by President Masaryk, and she spent one day in Jáchymov in 1925. She also spent some time in the shaft Svornost, and in her Thanksgiving speech, she mentioned that without the access to Jáchymov uranium ore, it would be very, very difficult to be the first to separate polonium and radium, because that time there were only 3 uranium mines in the world: British Cambria, Belgium Congo, and Jáchymov. So it was not easy to get access to the uranium ore. On our way to nuclear fission, we have to mention one man who made a very substantial discovery. It was James Chadwick, who in 1932 proved that there is one very important from the point of view of nuclear power or the use of nuclear power constituent of atomic nuclei. This is neutron. Without neutron, nuclear fission won't be possible. So the discovery or proof of existence of neutron was very important step forward. Then, on our way, we have to mention a group of German physicists around Professor Hahn. There were other very important members of his team, Dr. Strassmann, Dr. Meitner, and also other like Otto Frisch, and they in 1939 published a paper showing how uranium-235 can be split by slow neutrons, and also Lisa Meitner proposed a way how to achieve a chain fission reaction. Maybe it could be interesting that their paper was published in the Review of Physics on the 1st of September 1939. But this really spectacular in other case article was shadowed, completely outshadowed by the articles concerning the beginning of Second World War. Nevertheless, it was the beginning of a race for nuclear explosive, because we know that in nuclear reactions like fusion or fission, big amount of energy is released. It's roughly, we can say, 1 million more energy released in one nuclear reaction than it is released in chemical reaction like oxidation. What does it mean? What does it mean for the military service? Conventional explosives are based on very fast oxidation. If we think about having million times more concentrated energy, that means energy released in nuclear reaction, we can immediately think about possibilities to have million times more powerful explosive. So, as I have mentioned, it was at the beginning of the Second World War, when the discovery of German physicists was published, and the race began to try to get nuclear explosive and, in the end, a nuclear bomb. It was a big issue for Germany. They continued. France, United Kingdom, Japan, but the winner of the race were United States. On the picture you can see people that made it for the United States. Enrico Fermi, Italian refugee to United States because of fascist regime in Italy. Albert Einstein, Edward Teller. You have the possibility to follow their lives and destinies in new film by Christopher Nolan, Oppenheimer. And I would like to use this opportunity to recommend you Oppenheimer if you didn't see it yet. So, the team around Enrico Fermi put together uranium and graphite as a moderator, and on December 2nd, 1942, on the Chicago soccer stadium, there was for the first time when the nuclear reactor put together by people started its work. It didn't look very much like high-tech as we expect nowadays from nuclear reactors. But here we look on the grandfather of all reactors working now in the world. Yeah, United States succeeded. That means that on 16th of July 1945, there was first nuclear weapon test. It was called Trinity, and it has nothing to do with, I would say, Trinity as such, but nevertheless. It was a plutonium bomb, similar to that one that was used in Nagasaki a few weeks ago. The Trinity test was performed in Alamogordo in New Mexico. The place was chosen by Robert Oppenheimer. Here we can see Robert Oppenheimer with Leslie Gross, military chief of Manhattan, so-called Manhattan Project. The Manhattan Project was established to create atomic weapons. And then atomic weapons, and it was very, very fast development, in fact. Atomic weapons were for 2 times used to help to end the war in Pacific in Hiroshima. And 2 days after in Nagasaki. And I would like to mention now, say, Czech connection, because here you can see industrial palais in Hiroshima, created by the architect Jan Letzel. And this is quite interesting because the construction was so robust that it survived, even if this building was very near to epicentrum, and everything around it was really plain of much of rubbish, nothing else than this building by Letzel survived. And it's nowadays a symbol to Hiroshima bombing and use of little boy, the uranium bomb. I have just mentioned Nagasaki, and I will leave the nuclear weapons area soon, I promise. But still, I would like to mention that starting with the bombing of Hiroshima and Nagasaki, there were a period of nuclear weapons testing in the atmosphere, underground, in sea, and fortunately enough, people, mankind, was reasonable enough to recognize terrible destruction power of atomic or nuclear weapons, not to use them again in any conflict since bombing of Hiroshima and Nagasaki. But you can see that there were quite a lot of nuclear tests. The United States were soon enough followed in possession of nuclear weapons by Soviet Union or its successor, Russia, United Kingdom, France, China. Those 5 are by so-called non-proliferation treaty legal owners of nuclear weapons, with the commitment to slowly get rid of them, but it's not much successful. And then in the last quarter of 20th century, there are 2 countries joining this so-called nuclear club, India and Pakistan, and the last one to join this club is North Korea. So we have now 8 nuclear weapon states, with most probably there is a 9th one, but Israel never recognized the possession of nuclear weapons. Israel simply does not comment on that. Just to illustrate the amount of energy that can be released by nuclear fission and nuclear fusion, we can see here the comparison of yields of various atomic bombs. We can see that a little boy used in Hiroshima contained 64 kilograms of highly enriched uranium. What does it mean, highly enriched? More than 90% of uranium-235. And even more efficient is a plutonium bomb. That means we can see an example of Fat Man used in Nagasaki. Roughly 6 kilograms of weapon-grade plutonium. But of course, those nuclear weapon countries very quickly moved to combination of fission and fusion bombs called H-bombs with many times bigger yield. But now let's move to peaceful use of nuclear energy. It was soon clear that the heat produced by nuclear fission or fusion, but we cannot use it for the production of electricity yet. That is, it can be a source for production electricity. And it was soon after the end of Second World War and the use of nuclear weapons that the first reactor was used as a demonstrator of the possibility to produce electricity using the heat originating in nuclear fission. On the picture we can see experimental breeder reactor EBR-1. It was operated in the laboratories in Idaho Falls. We can see also that it looks very much like high-tech comparing to CP1 in Fermi's CP1 in Chicago. And we can also see that at the very beginning its power was very, very low. The heat produced by the fission reaction in EBR-1 was able to be used to produce electricity to light for 200 watts bulbs. The first nuclear power plant really supplying electricity to public network was was commissioned in 1954 in then Soviet Obninsk near Moscow. The power of the reactor was 5 megawatts. From today's point of view, it was a microreactor, but it was another step to prove that the nuclear heat can be used for production of electricity. We look at the US submarine Nautilus. It's not because I would like to go back to the military area, but the US submarine Nautilus was the first submarine powered by nuclear reactor. And the reactor for Nautilus was designed and manufactured by a famous American company, Westinghouse. And this was the first PWR pressurized water reactor, and this was the beginning of the family of most robust and most successful line of reactors for nuclear power plants. We will come back to it in a few minutes. First nuclear power station in the world to generate electricity on an industrial scale was a British Calder Hall. Calder Hall has the capacity to supply 50 megawatts of electricity to the grid. In today's terminology, a small reactor. The first unit was commissioned in 1956, and it was a big event. You can see on this picture, and you can find that Queen Elizabeth was personally present in the startup of Calder Hall 1. Calder Hall 1 was built in the locality that was called Windscale site, and nowadays it's known as Sellafield site, because we don't use, or nuclear community don't like to use Windscale anymore because of not nice nuclear accident in Windscale reactor in 1957. Back to US. Reactor powering submarine Nautilus was modified. Its power was increased to roughly 80 megawatts and was used in first US nuclear power plant in Shippingport in Pennsylvania. It was commissioned in 1957. But it was used not only for production of electricity. I would even say that the electricity was a kind of byproduct for Shippingport, and the main reason or the main purpose for Shippingport plant was to test various fuel composition and fuel assemblies for future nuclear power plants. So maybe the first real nuclear power plant in the US used purely for production of electricity was Yankee Row with 180 megawatt electric output, and on the picture of Yankee Row we can see that it had already all the safety barriers that we expect from nuclear power plant to make the vicinity of a nuclear power plant and people in nuclear power plant as well as outside the site safe in any case. This part is so-called full pressure containment. This is the barrier preventing radioactivity release in the case of accident. So you can see that the Western designs had those barriers preventing the release of radioactivity in the case of accident from the very beginning, from the 50s or beginning of 60s. Obninsk, Calder Hall, Shipping Point, Yankee Row, and other nuclear reactor designs were the part of so-called first generation of nuclear reactors, where various theoretically available options how to combine moderator for slowing down the neutrons, coolant, nuclear fuel were tested, and we can see that in this first generation there were several combinations of moderator, coolant, and fuel available. And from this first generation, so-called second generation, that means the winners from the point of view of robustness, safety, and economical parameters came out. And I have just mentioned that pressurized water reactors are a real winner for the time being, because you can see the share of various reactor types or designs built or being built in last 70 years, nearly 70 years. I would like to mention maybe that those in red are reactors working with graphite as a moderator, which is very specific for military designs, because graphite as a moderator enables to much more easily get weapon grade plutonium. We can see those are I would say typical for the fleet in the United Kingdom, and I have mentioned Magnox in Windscale, a reactor where the specific features of graphite, so-called wind energy, cost, overheating of graphite moderator, and the first nuclear accident with significant release to the environment. It was, and we have to mention it on the military design of reactors. So sometimes it's the Windscale accident is not listed in the list of nuclear power plants, civilian nuclear power plants accident. And you can see that what is being built now is in fact various designs of pressurized water reactors. I mentioned generations of nuclear reactors. I have mentioned also the first generation, we can call it early prototypes, and we have seen the combinations that were tested, combinations of moderator, coolant, and nuclear fuel. And you can also see some examples of power plants of the first or belonging to the first generation. This first generation was built from early 50s to early 70s last century, and those reactors were operated to approximately to the end of 20th century, some of them. But from those early prototypes, the most successful designs, as I have mentioned, from the point of view of robustness, safety, and economical parameters were chosen, and the majority of nuclear power plants operated nowadays in the world belong to, say, upgraded second generations. Most of the second generations are pressurized water reactors, where neutrons are moderated by light water, and the reactor core is cooled down by light water as well. In the mid of 90s, the market for new nuclear power plants was in fact saturated. That means there were practically no new orders for new power plants. Nevertheless, the designers and manufacturers didn't sleep, and in the mid of 90s, last century, that was the beginning of the development or evolution, I would say. Evolution is the better word, of so-called generation 3 or generation 3 plus, and those 55 reactors being built in the world today, those are the reactors of so-called generation 3 plus. I have mentioned that this is an evolution. That means that safety features, quality of manufacturing, simplifying the design, and so on, are improvements, gradual improvements of the designs of generation 2. If nuclear power should have a longer time future to serve us as one of the sources to produce electricity, we will have to move to not innovative but new reactor designs. It is called, this group of designs is called the generation 4, and it's expected to be built starting somewhere in the next decade. But there are several, say, prototypes of generation 4, especially reactors working on so-called fast, not slow neutrons, which can be used for fission not only of uranium-235 but also to uranium-238 or thorium. So those especially gas-cooled fast reactors are being built especially in China, also in Russia, also in India. But there are also another designs being explored in this generation 4, especially for more and more mentioned SMRs or small modular reactors. When we have a look on the development of world nuclear electricity production in the last 60 years, we can see that the nuclear electricity production step by step increase. When the generation 2 was introduced in 70s last century, it was partly a reaction to the first oil crisis, especially in France, I would like to mention. And we see that this increase since 1973 to 2017 was more than tenfold. Nevertheless, it's not enough. It's not enough because the annual electricity consumption in the world is 27,000 terawatt-hours. That means that nuclear as a low emission source of electricity can nowadays cover some 10% of the demand for electricity. Yeah, we can see it here. In 2021, in the world, 27,000 terawatt-hours was produced. Just for context, in the Czech Republic, the electricity production was some 80 terawatt-hours. That means that the Czech Republic has really a tiny share of electricity production. And nuclear electricity covered 9.8% of all electricity produced by the world. Slightly different numbers from what you have seen in my predecessor presentation. It depends when we count the reactors in operation. It depends on how we address reactors in Japan. They are in long-term shutdown after the Fukushima accident, and some of them International Atomic Energy in Vienna in the statistics don't list them as reactor in operation. That means they are not shut down permanently, but they are in long-term shutdown, so maybe it's more fair to list them aside and not include them in the reactors in operation. Let's have a look on Europe. In European Union, there are nowadays only 12 out of 27 EU member states with nuclear power plants in operation. In April this year, Germany finally stopped remaining 3 reactors in operation. So they joined the club of countries not operating nuclear power plants. We can also see that the installed capacity of nuclear power plants is not negligible, by far not. Again, I would give the comparison with the total installed capacity in the Czech Republic. All power plants, not only nuclear, it's approximately 21 gigawatt, out of which 4 gigawatt are nuclear power plants. Nevertheless, nuclear power plants operating in European Union cover some 22% of annual electricity demand, and most probably Europe would like, after some period of reluctancy, at least to keep this share, because it becomes more and more obvious that without nuclear, Europe won't be able to fulfill the commitments, what concerns the mitigation of CO2 emissions. Let's have a look on the countries with the highest share of nuclear electricity. Practically all of them are in Europe. World champion, France, 56 reactors in operation, and around 70% share of nuclear electricity. Slovakia, second country with the highest nuclear generation share, more than 50% of nuclear electricity in 2019, more than 65 nowadays after commissioning of Mochovce 3 unit. In fact, what concerns net zero commitments and the mitigation of emissions of CO2, Slovakia already fulfilled its homework, or nearly, because nowadays Slovakia has 90% low emission electricity sources. Nuclear, together with water, power plants, and a small amount of photovoltaic and wind power plants. Interesting, Ukraine relying very much on nuclear power plants, and if we still will have time, I will show you more information concerning Ukraine. Hungary, almost 50%, Belgium, almost 50%, but trying now to cope with the commitments of previous governments to leave nuclear energy and to shut down nuclear power plants. Belgium came to a conclusion that it won't be possible in next 10 years to close down the remaining nuclear power plants. Biggest operating country with 95 reactors in operation are United States. But United States, and we have seen it, has a very high energy demand and electricity demand as well. That means that 95 operating reactors cover only 20% of electricity demand in this country. Let me mention also low emission electricity generation by source. Because low emission electricity generation is of growing interest all over the world, even in countries like India, like China, like African countries. And we can see that by far in 2020, and it didn't change much since then, are hydro power stations, followed by nuclear, wind, solar, and then relatively low share comparing to solar has a bioenergy, geothermal energy, and the other possibilities are by now negligible. Again, I would like to remind you that the overall annual electricity demand in the world is some 27,000 terawatt hours. That means that still approximately 60% of this demand must be covered by fossil fuels. So let's have a attempt to wrap up what we have mentioned, and let's step by step get to Czechoslovakia and Czech Republic. We have mentioned already Obninsk nuclear power plant commissioned in 1954. We have mentioned US submarine Nautilus. We have mentioned the first nuclear power plant in the US, that means shipping port. And this is the time for mentioning that former Czechoslovakia and then Slovakia and Czech Republic didn't or has not played a minor or negligible role in peaceful use of nuclear energy. Already in 1957, in Czech, near Prague, the first research reactor was commissioned, and at the time, this research reactor was the 9th in the world. Soon after it, zero power reactor was commissioned at the same place, and in the 90s, the family of research reactors was to this family joined the zero power reactor at Czech Technical University, and we have now, since June this year, 4 research or educational reactors, because in June the second zero power reactor or subcritical assembly, better to say, was commissioned again at Czech Technical University. That means for the Czech Republic, medium size country, there are 4 research reactors. For comparable countries, it's a unique thing. What concerns nuclear power plant, the first one was commissioned, the first unit of it in Dukovany was commissioned in 1985. There are 4 units operating at Dukovany site. And in 2000, the first unit of Temany power plant joined, followed by the second unit in 2002. That means in our country we have 10 operating reactors. This is quite an achievement, I would say. Let me come back a little bit to uranium in the Czech Republic. Quite a lot was mentioned already. Nevertheless, I would like to mention what concerns Jáchymov a few moments from glorious history of this relatively small town. It was not small in the past, because there was a time period in 16th, 17th century when Jáchymov was the second biggest town in Czech Republic, or Bohemia, better to say. I would like to mention one thing. I don't know if it was mentioned or not, that in Jáchymov quite well-known, excellent people were invited to work in silver mines and to produce, say, very modern, or to establish very modern mining technologies. And the most famous one was Georgios Agricola. His work, called Terra Metallica, is quoted even now, especially in the United States, because quite a lot of technologies he introduced to, say, mining work are still, after some modifications, used. If you have the possibility to see his famous book, Terra Metallica, you will see a really beautiful pictures showing showing various technologies and also showing the very, very hard life of medieval miners. That means to see at least a part of the metallica is something worth doing. It was maybe already also mentioned that the Czech Republic was not negligible producer of uranium. We can see that taking into account the time period 1945 to 2007, the rank of Czech Republic was 9th in the world with 5% of total amount of uranium produced. Yeah, I have big luck to have the possibility to visit the last uranium working mine in Europe, Dolní Rožínka, which as well was the deepest mine on the territory of Czech Republic. Even deeper than the coal mines in Ostrava-Karviná region. This is some 1400 meters under the Earth's surface. And the last part of today's presentation, I would like to spend with the present and maybe some remark on the future, what concerns nuclear power in the Czech Republic. We can see that what concerns national mix of energy resources in 2021, 54% of electricity was produced in power plants burning fossil fuels, namely lignite, and some 10% was from natural gas. Some 40% came from nuclear power plants, those 6 units at Dukovany and Temelín, and approximately 6% from renewables. We should do better in the future, at least a little bit what concerns renewables. I have already mentioned nuclear reactors on the territory of Czech Republic. Here we can see them on the map, Dukovany, Temelín, and the localities of research reactors, Nuclear Research Center Czech and Czech Technical University Prague. So, to list nuclear facility, to give an overview of nuclear facility on our territory, 2 nuclear power plants, and there is a plan to have a new unit in Dukovany ready for commercial operation in 2036. I have mentioned research reactors. We have also spent and fresh fuel and interim spent fuel storages at both the nuclear power plant sites at Dukovany and Temelín, and 2 radioactive waste repositories there are plans and also projects to have deep geological repository for spent fuel in 2065. We can look at more detailed description for already mentioned sites. That means Dukovany. There is a power plant with 4 units, interim spent fuel storage. The difference is only in the name. The substance of the facility is the same. And low and interim level waste disposal facility. At Temelín there are 2 units, spent fuel storage and fresh fuel storage facility. In Czech, 2 research reactors, spent fuel and high level waste facility coming from research and development. In Prague, 2 training reactors, and in Litoměřice, 2 radioactive waste disposal facilities. We can also see more detailed information what concerns basic data of our 2 nuclear power plant sites. What can be interesting is that the former Czechoslovakia was able to build a nuclear power plant unit in 6 years. We can see that Unit 1 in Dukovany, there was a construction started in 1979, and unit was commissioned or reached the first criticality on in February 1985. This was not the case of Temelín nuclear power plant. 2 units at Temelín were or are typical delayed projects where the construction lasted approximately 13 years, which is quite long time period, but not comparable with already mentioned Mochovce 3 in Slovakia, where the construction and commissioning took more than 20 years. So this is the present of our peaceful nuclear power program in the Czech Republic. And what concerns the future, we will try, the whole nuclear community will try to build new nuclear units to replace step by step units at Dukovany. Units at Dukovany will reach their pension age, retirement age in 20 years approximately. And if we would like to keep the share of low emission sources, we will have to replace them. There is no other way foreseeable than replace them by new nuclear units. And we will look also for innovative technologies, especially nuclear designs with small or smaller installed capacities what we call now SMR, or small module reactor. These are units with installed capacity from approximately 100 to 300 megawatt electric. So you can think that they are not that small, but nevertheless they are much smaller than units that are today on the market. Units today available have installed capacity 1,000 to 1,700 megawatts. These are really big, with all the bottlenecks for financing and also for say organization of construction. So we will see, but I'm pretty sure that nuclear technologies and nuclear power will be with us, and we will be together forever, because nuclear power is here since the beginning, since the origin of our planetary system, and will be here till its end. Thank you for your attention.
Welcome to the afternoon session of the short course on energy materials. I'd like to introduce Dr. Juraj Franců from the Czech Geological Survey, who will tell us a bit about oil and gas fields in the Czech Republic, and later in second part we'll continue on other deposits.
Thank you for coming. It's a pleasure for me to be here with you. This is an outline. I tend to skip this because you will see it in pictures. So this is going to be about oil production. I will sometimes introduce Czech words because every day you see bad translations, usually from Czech to English and so on. So těžba is production, and we have two major regions, and that is South Moravia, we may say, and this is a typical wine and oil region. And there is northeastern Czech Republic, or Moravosilesia, and that is typical gas production area in this country. When we look close up to this area, we see this is from the internet of the Czech Geological Survey, Suroviny informační system, and there you can see the entire area and the different mining areas, we may say. But in general, this is where you find companies who produce gas in this country. South Moravia, really the wine producing is absolutely copying oil production. For some reasons, it is not only in our country. And again, this is M&D exploration area. And that means no other companies can enter here and explore for more oil and gas. No, because it is something M&D, earlier Moravské naftové doly, but now only M&D, where they have different oil and gas fields. This is outside. This is one of the most important underground gas storage. Dolní Dunajovice, there is another one, Hrušky here, but this is MND, partly with RWE. This is RWE company. So regionally, we are here. Map crossing border shows this is Austria, Slovakia, Poland, and Eastern Czech Republic. You see, oil is mostly produced here, only episodically here. And everything was produced by MND. Earlier, there were two companies historically. And this was MND Exploration Company. That means looking for oil and gas. While production, těžba, was Nafta Gbeli. And they were working together. Now, at certain time, they separated. So now they do exploration and production in Czech Republic, MND. I should mention there are like two microscopic companies that work in Poštorná, that is part of Břeclav, and another very little company is here, Unigeo in Ostrava, but they have Krásná and Janovice and things like this. But this is microscopic. So what is interesting in this picture, we don't see any oil and gas fields here. Why? Because this is crystalline or metamorphic terrain. Everything with oil and gas is related to Carpathians, West Carpathians and Carpathian Ph.D. below the overthrust unit. This is Vienna Basin going down to Austria, and there here was the first, I think it was somewhere here, the first gas field and then oil field in Gbeli, in German Edgbel, and then it developed mainly in Austrian part. You know, you probably used airplane from Schwechat near Vienna, and that was with Matzen, these were the largest oil fields in Austria. So we were always not that big, what we have here. This is interesting because this is mostly related to coal that is below. And it was believed that this gas comes from coal, and the production is in the Miocene of the Carpathian Ph.D. And but there are some very special things, like that they found that these gases are special, that they are different somehow. And nowadays we say, using isotopes and other special geochemistry, this is related to Carpathian world. And this has migrated upslope into the older units. You can find oil even in coal seams in this place. There is Stažič. It's already closed down mine, but there was oil. They found, miners found, they were dewatering the shaft, and they found there is oil on top of water. We analyzed that oil and found tertiary biomarkers, and that are completely related to Manilite shale that is within the Carpathian overthrust unit. So in general, there are different petroleum systems. What is the geology of the West Carpathians? This is the Carpathian Ph.D. It is in fact the youngest part, and that is the marginal foreland basin of the Alps and Carpathians. Our Austrian friends call it Molasszone. In Poland they call it Molassa. So even only we have, well, but they also use this Carpathian Ph.D. And this is the outer Flysch belt and the inner Flysch belt, so Maguras group and Ždánice Podslezská unit. So this is on top, and we, what Americans call subcrop maps, or stripped map. Strip is from striptease, and subcrop means not outcrop, but subcrop below. So what units do you see when you take off all the Carpathian allochthonous units? You see interesting Paleogene. This is Eocene of Vranovice and Nesvačilka. Jarek mentioned here important structural feature in Bohemian Massif. So this is the canyon filled with Paleogene sediment. Below is Jurassic, and I hope we can see it on the next. And on the north, you already see Carboniferous, large Carboniferous. So now if we take that Paleogene off and Jurassic, we see that there is also Carboniferous, and then there is Devonian, mainly carbonate rocks. And that's it. So when we look at a stratigraphic column, we see that we have crystalline, we may say, Precambrian, but petroleum people say crystalline basement. And then maybe we have here Cambrian. This is with question mark, but there are some remnants of Cambrian in southern Moravia. But then Devonian, those interesting, oh, these are these purple breccias, Babylon, and then carbonates of Devonian. This is a carrier rock. You can find some gas in these rocks. And then there is Carboniferous. It goes up to Ostrava and Poland. But here we see that this is not, there is some gas. Okay, very little oil. And then there is Jurassic, and these are interesting, first sandstones with shales, then some carbonates. This is Mikulov formation with marls, very dense rocks. They are impermeable, and they are principal source rocks in petroleum system of Eastern Czech Republic. And there are some carbonates above. So these are the major reservoirs in the southeastern Bohemian Massif here. And we see it with this green bubble. That means oil. This means gas. There is some gas. It should be put here. This was by Picha, so I didn't paint it. But and this flag means source rock. I will later get to that. That means in Jurassic we have also some source rocks, and these are the marls. And then Cretaceous in thickness, this is very thin, not that important, but there is thick Paleogene. Those are those Vranovice and Nesvačilka canyons, and they are at least 2,000 meters thick units, deep, not in the shallow part. So that's not negligible. Jurassic is over 2,500 meters thick in the southeastern part. And then there is Miocene, and that is the molasse. We have it here, even it is related to the contact of West Carpathians and Bohemian Massif. So, to summarize, petroleum systems always addresses is there any source, like source of uranium was mentioned here? So is there a source of oil and gas, or gas? And we can find that something in Devonian but poor. This may be quite good source of gas from the Carboniferous, and then Jurassic is good source rock. In fact, even in worldwide criteria, this Mikulov Marl is considered a good source rock of oil and gas. And finally, in Paleogene is another. When you look at those rocks, so this is dark gray, sometimes black. So that's typical color of source rocks. That means a lot of organics. Paleogene looks also very dark here and then. But they put here oil. Our geochemical analysis show this is gas-prone source rock. Very, very little oil potential for source. And then here, probably related to neogene, some parts of neogene have something like source rock, but much weaker. So that is the petroleum system already, and here are the two major canyons. It is wonderful to look into older literature how people conceived the geology. So there were, his name was Juraj, very nice name, very kind man, and he made a picture of Grand Canyon, and a vulture was flying over, and that was Jurassic, Nesvachilka and Vranovice, these two canyons. Of course, he didn't say that's the only truth or only possibility. Frank Ph.D. worked for Czech Geological Survey, then moved to Chevron in the USA, and worked probably 30 years in Chevron. And but he was, while he was at Czech Geological Survey, he said these are typical submarine canyons. If you were learning basin analysis, you know what are submarine canyons. Big rivers continue in the sea, and they carve 1,000 meters deep canyon in the sediment, in the shelf, or much even deeper. And he collected evidence for that this was in a deep sea, not at surface in dry land. So this is the Paleogene, and when we look at the cross-section going from Vienna to, not to Poland, but in that direction, we see these two valleys, we can say. Incised valley is a sedimentological term. So filled with orange, that is Paleogene. And Jurassic is here, here, and here. We are now working on Jaroshice, and that is Jurassic, and it's somewhere here. But just for you to imagine, this is Drábová, Užice oil and gas field. That is the top Czech oil producing field. The amount of oil produced in Czech Republic, it's like 80% or more produced from this place. So different strategies need to be organized to find such big oil fields. Now, when you look at the sedimentology, so this was the canyon. It was carved into Jurassic rocks. They should continue like this. They were eroded by marine river, continuation of river. And then there were different rocks deposited in here. The typical feeding by sediments was this: slumps, sesuvy česky, into the deeper sea. That means no stratified, nice strata, but one can say more now. But that's too strong word. And what is important, at the very bottom, you see reservoir rocks. And it is often very difficult to distinguish, is this already Paleogene or is it still Jurassic? So that's why, for instance, Užice field was considered Paleogene. Now they say it's Jurassic, Graston Formation. Let's move on. So, the perpendicular section going from Brno to Slovakia to Bratislava or something like that, you see this is crystalline basement. And then Carboniferous. Here you have Drahanská vrchovina, Carboniferous, so that's the early Carboniferous column. This is the upper Carboniferous assumed, because it has been and has not been fully proved, but Carboniferous. Then a lot of erosion, and then Jurassic, blue. And Paleogene, pale orange here, and everything above is allochthonous. That means overthrusting of West Carpathians. Do you have idea how far was the overthrust in terms of horizontal distance? Guess. 200 kilometers or more. And these units, this is Magura unit. So that is even more, maybe 500 kilometers away from here. So it is tremendous. And one word is very good, and that is thin-skinned tectonics. Can you imagine that this is a system of thrust sheets, and they have been moved in a deep sea, 200 kilometers. Can you imagine that? How such a thin piece of body can be moved onto an old continent like Bolivian Massif. The final piece of geology is Vienna Basin, and that is superimposed on these Flysch units, Magura unit here. And you should imagine that the Carboniferous was the upside down. This piece of Carboniferous rock was shallow, and these were like 5 kilometers deeper than today during the very last Carboniferous era. So, so this is a big change in that. Jurassic was buried, pohřbený, a terrible word, but simply covered by new sediments. It took like 1.5 million years. It's almost nothing. And it was from here, and it was here. So it was very rapidly buried down, exposed to much greater depth. And here we are at 10 kilometers, almost, yeah. I see it from not the right place, but I know that the deepest sediments here are over 11 kilometers deep of the outer Carpathians. So we have oil here in the Jurassic, and this is Neogene Carpathian Ph.D. So there are some oil and gas fields also there. And then we have in Vienna Basin, and the source rock is blue. Can you imagine that oil migrated through these thicknesses and made it up to the oil, to the Vienna Basin? So for instance, they say Tinec, but Hrušky is something like here. And all this oil and all the Austrian oil comes from this Jurassic source rock that is down. I will show a picture later. So, so petroleum systems provide answer why somewhere you find oil and gas and why not in other places? The biggest sedimentary basin in Czech Republic, who could tell me? Which basin is the largest in Czech Republic? I would say Cretaceous, Czech, Bohemian Cretaceous basin. Is there oil? There are perfect reservoirs, absolutely perfect reservoir properties. There is absolutely no oil, and even gas is missing. Why? Because petroleum system is not complete, there is no source rock, and there is no kitchen. What does it mean? Petroleum system was published in 2002, but maybe 10 years earlier, something. And it says you have no oil and gas if you do not have a hot kitchen. And you put active source rocks in a pot and heat it and generate oil and gas. Like on Sunday you cook lunch. So you need to do this somewhere in the nature. And then the fluids migrate. If there is a seal preventing to escape, seal is not perfect, so you have partial escape. But something makes it to the trap. And the trap means a reservoir rock with a cap rock. Or a structure, it may be formed. So there must be good migration path and must be a good trap. So, and all this needs perfect timing. Making Sunday lunch at 6 o'clock in the evening is sort of late. So not good timing. So the same you need. The principle number one is you always need to have traps as if ready or almost ready, and then start cooking. If you cook and there is no trap here, everything will go to the atmosphere and away, never form an oil field. So trap should be first, and then should be heating and cooking. This is an example from Alaska, North Slope, Alaska, and this is a computer program. In fact, you have Petromod and here in Kotlarska. We have it in Czech Geological Survey, and it makes it possible, to show that you have a source rock. You have 20 layers, 20 strata, and one is good source rock, as is shown here. The colors show thermal maturity. So these are immature and these are mature. This is so-called oil generation zone and wet gas generation zone. And you may simulate what happens in the nature, and that is how oil and gas migrates to the shallower strata. And finally, how they accumulate. So nowadays, big companies or smart companies do this modeling of the petroleum systems, and they can even calculate what will be the composition at different depths. And so you see here that this is an oil accumulation, and here is an oil accumulation with red cap, that is gas. It does not occur deeper, because like Coca-Cola, when you open it, bubbles go out. And you don't see, when it's closed, you don't see bubbles. So that's called bubble point when you open Coca-Cola or Coca-Cola. Yeah? So open it, lower the pressure, and you make bubbles, and gas separates from the solution. The same happens in oil and gas accumulations at different depths, and that means lower pressure exsolution of gas from the solution. Now, so who are the principal parts of petroleum systems? Source rocks means that the amount of liquids and the fluids in general must come from something. And that's not magmatism in our case. And these are dark rocks. And we will see, you can address this quantitatively, that you measure how dark are they, that means how much organic carbon is there, how much hydrogen is there in the organic matter. And this is a typical scheme of kerogen types. Kerogen is a insoluble, non-moving black rubbish in sedimentary rocks. And it may originate from different biological sources. So we say that the typical coal is here. Coal, land plants, and if they are without cuticles or humic coals, so they will be here. So these two are called kerogen type 3 and 4, source of gas, not oil. While these two are oil prone, and these are made from algae that's something green, like in Brněnská Přehrada. You have silice, so they are blue, green algae. But algae means something what lives in water. It's ugly, it's not very friendly. And phytoplankton is the same thing, but floating near to the water level. And this is the largest biological production. It's much more organic matter produced in the sea than on the land. This has been calculated and proven, and it goes into sediments and accumulates, so incredible amounts. And if you can imagine that 10,000 units of source rock will produce 1 unit of oil. So the efficiency is low, but the gas fields in the world show this, that they have very specific relationship to source rock. This is that at the beginning, the biology is here on the right hand. So living plants here, living algae here. And diagenesis and catagenesis, that means when it's covered by other sediment, make it more thermally mature, and it shows here by lines that you have less and less oxygen and much stronger, less and less hydrogen in organic matter. And they use terms like kerogen is immature at the beginning, then which is early oil window, peak oil maturity, that means oil generation, and wet gas generation and dry gas, that means without oil. We have microscopes, we have fluorescent microscopes, and we can see what does it look like in a thin section or a polished surface. And this is what the, we may say, more primitive organisms, what they look like. Like these are floating, that means phytoplanktonic algae, and these are typical algae that makes algal mats. You probably go to a dirty swimming pool and you slip because there are algae on. And this is the typical algal mat that is making, or stones are covered by algae, or they, if you dive into Brněnská Přehrada to the bottom, or somebody dives and gives material to you, it's full of this type of organic matter that is aquatic, and it's excellent source of oil if it's buried 4 to 6 kilometers deep. Now, what is this thermal maturation? It happens in rocks and in coal parallel. And the next talk will be about coal, so brown coal, bituminous or black coal, and anthracite. And there is a parallel that if you drill a new well to a sea, to a shallow sea, like for instance Norwegian, that is North Sea. So first you find a lot of methane that is related to microbes generating methane at low temperatures today. Then you reach oil generation window and you start to find liquid oil. Then the liquid is very light, like gasoline, benzene, and then only dry gas. This is what Franců published in '89. This is East Slovak Basin. And within several wells, the repeated story told the same. So this is immature Franců, and this is very mature, and this is over mature. That is, that there are a lot of liquids and gas is being formed, and you can measure it, that you find volatile hydrocarbons in the rocks. Whatever rocks, if they are a little bit more rich, you can see. And then in the very deep strata, you find only dry gas. And so this has been shown. These are in fact Rockawell pyrolysis data from that. And that was specific because there are wells, and Trhovište 26 encountered 206 degrees centigrade at the very bottom at 4.2 kilometers depth near Michalovce. And so you could see it in samples, everything. And this on the left, it is so-called source potential. You want to go to Croatia for vacations, you take a car, but you don't have gasoline in the car. You will not make it to Croatia. You need to fill the tank with gasoline so that the engine can work. And that's the same here. This is that the source potential is like that the nature provided this amount of fixed hydrocarbons in the structure of organic matter, and with cooking, and that is the oil generation, cooking takes place here, and you reduce the source potential into almost zero. And here are the temperatures, so 80 degrees, 130, 150. These are key temperatures. It depends if it's fast, or you know that the best food is not made in 5 minutes, but for instance 2 hours slow beef roasted, it's the best restaurant. So time plays also a role, but in general, if you have less temperatures, you cannot make it. So again, question. Tell me, is this temperature encountered by any well in the Vienna Basin, 130?
I believe so. I think so.
Yes or no?
Yes.
No. 4 kilometers, 115 degrees centigrade. Those wells which made it to 4,000 meters, they had only 115. So that means basins are different, and in fact these 200 degrees, this could be like 4 kilometers in the East Slovak Basin. So basins are different and make different petroleum systems. So maturity, thermal maturity, going from immature to overmature goes different way. And here we have Pannonian Basin system, and in fact this is from the East Slovak Basin, but Derečke or Holt Mezővásárhely one in Hungary, and they reached this value at a very similar depth. And this is vitrinite reflectance, I have to explain. And this is Vienna Basin, so they are almost the same age, going from lower Miocene to Pliocene. And big difference because heat flow or heat supply is different. So this is something you can measure by microscope, and it's a very widely used scale to say about thermal maturity. And the previous picture has shown Vitrate reflectance 0.6 is a very, very slow beginning of oil generation. 1.3 is the end, or almost end. And here you see that in Vienna Basin at 4 kilometers, still almost nothing goes on. So all the oils are of much higher maturity than the rocks you can find from drilling cores. Now about migration. So that was the source rock story. Migration means carrier rock. Prodrenage. I don't think we have a good Czech term for nádržní horniny, could be, but it's also strange. So carrier means that migration goes through wells. What is important? The colors are not very clear. What else? You cannot see it very nice, but you see that there is oil here, and the wettability property is the key. Certain rocks like carbonates and oil have completely different relationships or wettability than clay or shaly sandstone. So the story will look very different if there are different grains of rocks, if the pores are big or small, and if the communication goes well. So laboratories make good monies when they measure capillary entry pressure. And that is how much you need to push to get the fluid through the rock. Now, everything is now being modeled by computers. So this is a typical section. These are different strata, and here is the source rock. And here is the pore space saturation with liquid hydrocarbons. You can simulate that with computers, and here you see that the migration from here goes here, and even from through here there is a fault. You may expect some migration here, but you end up with saying this basin has perfect drainage setting. That means the efficiency of migration will be very high. Or this basin has very good source rock, but very poor migration conditions, and therefore much less oil and gas fields there. This is another type, so-called flow path modeling. You can Google it. People are using it for hydrology, people are using it for oil and gas, and it's copying topography. That means this is high, structural high, and this is deep. And the program simulates like upside down rivers. You can imagine that these are rivers. This would be high and this would be low. So rivers, many brooks put together a river and a bigger river and so on, and lakes. So the same story but upside down is that gas and liquids are migrating, and if you have a structural trap here or trap here, you make accumulations, and this is called spill point, where this accumulation is overfilled and more oil migrates further to another accumulation. So these are tools that maybe that are being used today by petroleum companies, and the most sophisticated migration accumulation story is shown here. And this is the source rock that is red. That means already dry gas zone. This is oil maturity, and you see how much oil is migrating. In fact, this is a picture I got from South Brazil. This is Brazil Atlantic offshore. And here you see how many accumulations may be formed, and it may be full of mistakes. But if you have drilled data, and they have like several hundreds of wells here. So they can correct the model that there is no anticline here, or there is a fault and it's not permeable, or there are whatever other reasons, and you make more and more real models of the geology. And so what are the accumulation types? This is the most simplified textbook by Bjørlik, a Norwegian professor. And so this is a typical anticline. Why? Whatever reasons. Geology makes fun, so makes an anticline. And you see now, sorry for the colors, but he made water yellow and oil blue. Should be upside down, but so this is an oil accumulation. And there is aquifer, that means the water below oil. This is the same type of trap, but you have a spill point. If you go to toilet after this lecture and you flush, you use this principle in the toilet, that it is the spill point and you get something away in this direction. And here the nature goes that there is more and more oil and some gas accumulated here, and when it goes down here, it spills, that means migrates further on and migrates to another place. We have now, in fact, the fourth project with Norwegians, the Czech Geological Survey. And we are working on storage of carbon dioxide in a depleted oil field. And the key question is, where are the damned spill points? Because if we store, and suddenly CO2 goes to that neighbor's garden and his room, he will be angry. So we should be very careful what might happen if a spill point is overfilled. So that's structural trap with closure, that is this, and spill. Fault-related trap, the typical from a Hrušky field. Hrušky is the largest oil and gas field in Vienna Basin in Czech Republic. And you have faults, in fact they are growth faults, so it may be Sarmatian strata and deeper Bladanian, the same stuff. And simply what is important that this fault separates different permeable and impermeable rocks, and this is reservoir, but on the other side of fault there is only impermeable rock, so this is a closure. That means trap. If this yellow stuff would touch here, so all the oil and gas will escape through here. So that's how faults play important role, because in fact in Vienna Basin, if you drill a well here, you won't find any fault. You would see just sandstone and clay, shale, but never something you see in uranium mine, yeah, or things like that. These faults look very different in fresh, young sediment. But this is a structural trap. And computer, this is again Petromod, is showing how an accumulation forms, and these are the migration pathways, and this grows. And if you look it through a million years, you see how this is growing, because conditions are favorable. So how to make the exploration to find all these things? And so these were the processes we want to address, we want to hold, and how to do that. So since sorry. Since 1930, this picture was made that true men marched with geophysical instruments several kilometers in hot or freezing weather. So men are incredible creatures, you know, sometimes. So this is an instrument to measure, to make seismic sections. Can you imagine that? Nowadays, I think things look different. So the #1 exploration work is done by seismic survey, seismický průzkum. I will say it in Czech. Seismický průzkum is something where you make cross sections or structure of subsurface. Seismologický is about earthquakes. So this is not to be confused. There are different tools and so on. So very easy situation offshore. Nowadays, a boat flows, goes on water and makes a seismic survey, and you have to have geophones, or you may let them float, these geophones. And in this principle, it's almost the same like if you go to a doctor and he makes with ultrasonic device on your belly. The same idea, same technology, just different power. And from that, you see the ship with those making noise makers, so sources, and then geophones. And onshore, that is our country or desert here. You see, the guys must bring kilometers of wires and put geophones here, and then comes a truck, and this is a hammer. So the wheels are lifted and hammer makes like this. People don't like it. Imagine that a series of 30 such trucks start to make this noise near your village. You may say, I hate oil companies. So it's not that easy. But what you get, maybe you have seen a doctor's screen of your belly, or a pregnant lady can see her baby, or a father can see his wife's baby. In this way, the same thing is here, that you have layers of time horizons, and from that, nowadays everything is done in 3D cube, so there are inlines and crosslines, and from that you get a great mess, but when you organize it, you get a nice picture, and finally you get a series of many profiles. And these profiles are sometimes better. You see some horizons here, yeah? Here, this is strange. This is probably crystalline. What you do as the next thing, you make the seismic well of data tie. Tie means to put together. This is measured in wells. You have some exploration wells already, and you are able to show it everything in two-way travel time, that is the ultrasonic or seismic time, and you can correlate horizons. And from that you can start to say, this is Pannonian and here is Sarmatian already. Or here is transition to Badanian. So that's the key important message, because from the wells you could do some paleontology and so on. So you make correlations, and from that you make pictures like this. This is one of the star of M&D company, Vladimir Opletal, and he made this picture from Jaroshice field. Jaroshice field is this hump, and there are wells going from different trajectories. Some were almost vertical, the newer are more horizontal, and from all this information he is able to make the topography, that means ups and downs, or a contour line maps of this is top of Vranovice Formation dolomites. Yeah. So things like this, and if a trained person is able to do such interpretive modeling, he is able, or she is able to make like 20 layers, horizons. And so that was seismic and supporting geophysical data. Now, gravimetry is a wonderful method. It's so cheap when compared to seismic. You do not make no noise, you just go and bring a box and put it and measure the G. That means what is the gravity number. And from that you make so-called Bulgur anomaly maps, and they show, so red is typical crystalline and blue is typical thick sedimentary package. The area, this is Vienna Basin. In fact, this is Austria. This is border. Yeah. So all this is in Austria. Sedlák. Jiří Sedlák is the chief guy in Czech Republic of gravimetry. Now, what is interesting? You measure the density of rocks, but you can make a derivatization, and that means show the horizontal gradient. Yeah? And this shows where the big changes in density occur. And this is mapping of deep faults. If any one of you works with structural geology, so this is Steinberg fault. Steinberg, and this would be Schattenberg, the next one, and sorry. So while no major faults here, and this is the deepest part. So the deepest part of the Vienna Basin is here, and gravimetry can show us what are the shapes of those sedimentary bodies. Sorry. Now, wells. The next tool is drilling. Much more expensive than seismic or gravimetry. But you get hard data. And we could go through, but I think you are going to visit the drilling site, and you will see this is an oil rig, and these are hoses drilling mud down to the hole, and then this is rotating, or nowadays rotation takes place down, the motor is sent down, and so there are other interesting parts of wells. Sorry. So this was in Velké Bílovice, going to Břeclav, and this is the rig, and here is the platform. You are not allowed to go there. This is too dangerous for visitors to go there. Only trained people can go there and see it. And here are the rods, drilling rods, vrtné tyče. And they pull it up here and then connect it and drill down in that way. And here is the guy from MND, and this is a Czech student from Masaryk University. Other students, and this is the container for mud. Mud není bahno, mud je vrtný výplach. You will see the mud goes down and it brings rock cuttings. They are like 3 millimeters chips of rocks, and they are collected, and this is the major source of information what rocks are there. And yeah, this is the hose, yeah, pumping the mud and let it circulate. So this is the drill bit, that means vrtná korunka, and the mud suspension goes in, and along the casing, podél pažnic, goes upward and brings all the material to the top, to the surface. This is typical to make core. That means that you get a barrel of rock, vrtné jádro, while these chips are vrtné úlomky. So, different drill bits. Then, when they drill, they send downhole well logging equipment, and you get fantastic set of data about the rocks you are drilling through. And there are also very important things that you need, at every second you need to know where are you in XYZ. And then you have well logs like a neutron, a gamma ray, caliper, and so on. And if you, those of you who are going to visit the well site, so this was the guy, many screens and all the data from the drilling he could check and control how to drill and how to work with it. They love this job. You will see that they live with it, and they make incredible documentation of the geology in the subsurface. You can work with microscope and look at the rocks if they are good reservoirs. So this is a typical thin section of a dolomite, and here is blue epoxy that was impregnated into the sample, and it shows how big are the pores or fractures in the rock where oil and gas can move. You can use isotopes that are fantastic for gas geochemistry, and you can distinguish. This is a section of the Vienna Basin with all kinds of different, this is already Slovakia, Triassic deep, for almost 5 kilometers deep reservoir in Triassic, and you see it's very heavy isotopically. While at shallow depth, 1.5 kilometers, there is, this is very light, and this is too light, and that is because microbial recent methanogenesis works and changes these gases into half biogenic, half thermogenic. So again, something about thermal maturity of the fluids. So I visited Strasbourg University, a geochemistry lab, and there was a fantastic student, a girl, and she made about hundreds of crazy cartoons like this, and explained very sophisticated things to show how organic geochemistry is important for oil. Oil correlation or oil source rock correlation. So this is a molecule, this is a styrene. You know what is testosterone probably, or ergosterone. So these are typical hormones, and the only thing that they have here, OH, and that is in geological conditions cut off, that hydroxyl goes, and otherwise it survives. We can find styrenes 400 million years old in the rocks. They are there. And from that you can say what is pedigree. That means who was the father, who was the grandfather, grandmother, and so on. So that is that you can say it for oil and you can say it for source rocks. And you can compare and say, so this is the detective comparing two chromatograms, and he's also styrene based. So he can correlate and say, this oil is not from this rock, it is from this rock. So the father is here, not here. So that is important, and then there is thermal maturity again. Yeah? So immature baby and over mature pracující důchodce. So that can be read from the geochemistry of biomarkers. And from that you can make conclusions on migration pathways, and if from here or from here. So that all this is used. In fact, this was in Strasbourg, and this was for French company. So different companies, it is not only for one nation. Now, what you do, you have hundreds of data. What to do with it? How to organize that? And there are simple tools. Every student may like it. Within 15 minutes, you may learn how to work with multivariate statistics. Even free software exists, or you can buy a very cheap one. And you make cluster analysis. You put there like 50 parameters, and you want to see who is similar to another one and who is very dissimilar from others. So you put all samples here, and you see that this one, this group, is the most different from all the others, while this group is almost the same, or this group is very, very unique group. It is almost one family. Here they relate it to high stand, low stand, transgressive system tracks. If you had sedimentology, you may understand these words. But these petroleum geologists are knowledgeable of those things and can put geochemistry as a part of it. Now, when you make a job, you always run into accidents. Only idiots do not have accidents, they say. So it may always happen that you run into a problem. And so what to do to prevent such a bad situation? You may remember Macondo. Where is the word? Macondo is here. Yeah, this was in Gulf, north of Cuba. And exploded the platform, 11 people died within 1 second. And why this happened? Because they drilled overpressured zones. What does it mean, overpressured zone? Is shown here. This is depth, and this is pressure. Hydrostatic pressure, everybody knows that if you have such a long tubing of water, you will have this pressure. The same applies for lithostatic or geostatic pressure. 2.4 kilograms per cubic decimeter, and that is the gradient of this green line. And the fluids make blum, blum, blum. This is hydrostatic. Sometimes when you produce a lot, it goes even below hydrostatic. But in the nature, this occurs, that suddenly this is an overpressured zone. If you drill here and you do not expect it, you blow out. This was in Gulf Coast Sea, and it was a big accident. Films were made on that. It took them from May or April to September to fix it. Can you imagine, with today's technology, they were not able to stop it. And there were reasons why that happened. But you may go to Břeclav, and going north from Břeclav, there is a field, and they drilled, and suddenly, 500 meters away, the steel pipes were shot to heaven because it was connected, and it was simply, they drilled an overpressure horizon. It brought gas here, then it went 300 meters deep to the other side of the field, and then and it was at 5 o'clock in the morning, and thanks heaven, nobody died. But if there were people, they would die immediately, because this was a very difficult explosion. In East Slovakia, like 1,000 tons of steel was in the air, because they drilled overpressured horizon and were not ready for that. So accidents must be very, so this is the area, Moravian Central Depression, part of Vienna Basin, and there are, in the Bedanian horizons, it is overpressured. So they are, it's tricky to work there. But you can think about it and do something to prevent it. This is almost the end. So we know what is petroleum systems. We have seen some fields here. And now a typical thing, so what is the history of production? And so production těžební historie, and you see that at the very beginning, this is in 1960, so 1960 to 1965, and this is by months, if I'm correct. Yes, and they produced that much water, that much oil and gas. They produced much more gas. They had to stop it. They had to cement and drill and perforate deeper, because the gas is pumping your oil to the surface. Otherwise, you need to pump it and spend a lot of energy on pumping. So they cut off the gas production, and they had oil production. Something happened here, and they had a break. Then they continued, but more water, and suddenly almost don't see any oil here. So they closed down 1965. So that's very typical what happens with the production history of oil and gas. And when we look to statistics of oil production in Czechia, so this was 2003, not that far ago. And this is the decline, and today it's somewhere here. So, what is the future? We will see. But this is the total for Czech Republic. So, what to do with it? Yeah? And this is in barrels, and here it's in tons. So thousands of tons per day. 200,000 tons per day. It's quite a lot of money still. So they are still making some money, but it's thinning and thinning. And so future, where to go? A lot of energy in the world is focused on enhanced oil recovery. Česky terciární těžby, sekundární a terciární těžby ropy a plynu. And increase from poor 25% of oil, which is in geology, to put it to your tanks, to increase it to 38 would be a big financial success. Then CO2 storage in depleted oil and gas. In Czech Geological Survey, we have 15 years Norwegian funds and European funds for CO2 storage in Czech Republic. Emissions, you have heard, you know what is climate change and so on. So enormous money is put in the world, in the Western world, to see carbon capture and storage. And storage means you deplete the field, and instead of that oil and gas, you put there CO2. Because CO2 was always in subsurface. All these bubble waters and so on. The next trend, hydrogen storage. You can open the newspaper, you can turn on radio, and you see hydrogen economy will save us. So, what does it mean to make hydrogen from water that's very expensive, or by sunlight, or from methane, it's much cheaper, and store it, otherwise you get povolenky. Povolenky, that means you have to pay for emissions. So not to pay for emissions, let buses use hydrogen, hydrogen cars, hydrogen everything. So to store hydrogen in underground gas storages, very modern trend, very little is known about it. The most interesting thing is they stored a lot of hydrogen somewhere, and next year it was gone. It was simply not there. And what happened? There are answers, but will be surprises, and there will be new things to be invented. And finally, geothermal energy. Every well, and we have from Austria to Poland on Czech Republic territory, we have over 4,500 deep wells. Many of them are cemented, but still many are active. They could be used for geothermal energy. That means not do only one job, but while you do this, you may side job, and that may bring you more money than the original intention. So geothermal energy, heavily subsidized by state governments of the West, pay a lot of money to support geothermal energy. Hydrogen storage, millions go into that. Millions go into this. So the companies start to think about why not to go into such business. Thank you for your attention. Coal in Czech Republic, we have brown coal, brown coal fields, and they are in the northwestern Czech Republic. There is some lignite, no more active, but used to be here. Nikolčice in Vienna Basin, and then we have what we call black coal, Americans say bituminous coal, and that is northeast. So what are the coal types? They are starting from peat. You can still find plants in peat. Then lignite is already sort of different, and it's brownish. Then there is bituminous coal, in German Steinkohle, or hard coal, or black coal. So that is black, and it's here. And then it's anthracite, that is silver. Finally, everything turns to graphite if it's metamorphosed. So coal petrology tells us what is it composed of, or what builds the material of coal. And like minerals are in inorganic petrology, in coal petrology they use words macerals. From maceration, and it is something juicy and you extract something, so they prepare these pure organic macerals using some chemicals. But you can see it in microscope without changing it chemically. And you can see this alginite I mentioned before, and some coal is rich in alginite, and that is yeah, I will get to this name, but simply algal rich coal. Then vitrinite is from French word for glass, that it looks very homogeneous, like a glass. This is translucent light. This is cutinite. You know what cuticles are. Leaves have a waxy cover. Especially tropical leaves have very waxy protection, not to dry out, and that is called cuticula, and that turns to cutinite. So in reflected light microscopy, this is typical vitrinite, grayish, not very fascinating, but homogeneous matter. And when you measure reflectance, that means what is the light reflecting from this material, you can say if this is lignite, brown coal, bituminous coal, or anthracite very easily. Here we see inertinite, and this is close to charcoal. You make barbecues using charcoal. So that is the other part. So cutinite may look very beautiful when you look at it in fluorescent microscopy, fluorescent light. And this is another piece of coal, and here you see cutinite. So you see the leaf with its cells, and this was coated by wax, and this wax make this shape of a folded leaf. Resinite means the smula, what fills the voids in wood or leaves. If they have full of resinite, some leaves, some plants have a lot of resinite. So these are things that are very visible in fluorescent light. And they are in fact very good source of liquid and gas hydrocarbons. When the thermal maturation goes on, or you may say coalification. So another example that you see, this is these are cells of a partly wooden tissue, and there was some resin in these voids. So this is what it looks like when you find it in microscope. Now, what are the depositional systems? So they are raised bogs, vrchoviště or fens or mires, slatiniště, that means much more water. You have water level. You can see some animals swimming on top of this water level. And this is not very acidic, while this is acidic. If you go to Manchester, they have a Lindo man. Did you hear about it? They found 30,000 years old human body in peat. And because the Lindo was the local name, where did they find it? And simply the poor guy fell down into this water, and the humic acids petrified him or mumified him. So this is typical for this type of environment. This is another example where coal is formed. This is an intramountain valley filled with wetland, probably used to be a river here, and brownish moss or these plants that make peat, finally čili rašelinu. And in fact, this is one of classical type of uranium, organically bound uranium. You don't find anything with gamma spectrometer. You can find it chemically that there is a lot of uranium here in this type of environment. If these rocks are granitic or a good source for uranium. So that is the coal and uranium often goes together. And that might be the Cretaceous coal we have in northern Bohemia. So what does it look like? And we find a lot of biology there. So you go to Bílina, fantastic place. you will definitely visit the museum they have inside Severočeské doly building, and you see maple, willow, and ferns with nice preserved leaves, or bugs like cicada insect, or some oyster, or this is pine cone. So fantastic things can be found, and these are maybe coal seams, but maybe also clay interlayers. And this is interesting because this is amber, that means resin from that wood, and that amber is jantar. Czech amber is called duxite from Bílina coal mine. What are the modern analogs? You will visit Bílina, and there is chief geologist Karel Mach, a perfect guy. He took his wife, they took a canoe and went to Okefenokee Swamp Park in Georgia, Florida. And so they were paddling the canoe, and he was observing the trees that are identical to those found in Bílina, Taxodium. And then these Lechnini, I even cannot say now, but macrophyta plants, water plants, and he has many pictures of these guys who are in Okefenokee. We don't have that in Bílina, so don't be afraid visiting Bílina. And then codification. Codification means that we get the peat, then brown coal, down to depth of several kilometers. And here is a history how this happens. And this is, I think this is Darkov, or the next one. So that is near Karviná. We are going to visit on Wednesday. So this is the burial history and thermal. This is by computer made how the layers were pushed down to depth and then uplifted, and currently they are at this depth. And you can do this because you know how vitrinite reflectance, how the thermal maturity goes in certain well. So from that you can, like with apatite fission tracks, apatite fission tracks can model you the uplift part, while vitrinite can calibrate the downgoing, that means burial of it. And this means that how come that at certain depths of 1,000 meters you have vitrinite reflectance of 1, you should have it at 3 kilometers at least. So this is how the burial and uplift history of regions can be modeled using coal petrological parameters. So first brown coal, Bílina. It is largest, and you see that to get 1 ton of coal, you have to remove 10 tons of overburden. And that is sand, gravel, clay. And nowadays, it's a big business. And it's going to be the major business to sell all this. There are no more quarries open in Czech Republic. If you want to build a house, if you want to make a road, you need building stones, and they are here. So they are going to sell this. They dumped it on the right hand. It's not shown here, but it is like this. On the left side, they excavate, they dig, and they depose here on the other side. So they found that there is an excellent clay here for remediation, to make the damaged country again green for tourists and for everything. So they put the best clay because they can sell it or they can get money for that, they can make business. And so, again, if you are focused only on coal, you will make less and less money. But if you take it all together, you can live next 100 years. So this is what it looks like from satellite. You will come probably here. You will enter the mine like this and see this. This is 4.8 kilometers altogether. But you see, this is like 3.5 kilometers from left to right, and from here to here, it's 4.8 kilometers. And the hole is 200 meters deep. It is the deepest surface in Czech Republic. If you measure GPS, XYZ, so this is below sea level. Yeah, so that's how big it is. Now, the thickness is up to 30 meters thick. This is fantastic. Not fantastic, simply a lot of coal. It is not everywhere like that. Even Germans in Westphalia, they envy this. They don't have such good coal fields. Between Köln am Rhein and Aachen, there are big, very similar, same age gold fields, but these are better. So this is what it looks on the map. The important point is this is Bílina. This is Most Basin. Altogether is Most. And these are mainly sands of the Žatec Delta. When you look at the section from west to east, so you see that the coal seam was in fact horizontal originally. But you see the tectonics worked, and it's deformed, and it's very much uplifted here and also here. So there are different depths, and they had to remove everything above the brownish stuff. So very interesting three-dimensional geology. Karel Mach is an exceptional geologist. He is now building for almost 30 years a 3D model of Most Basin. Fantastic with computer, because how they proceeded with digging and production, so he put everything in computer. So that's the stratigraphy. There is coal, there was volcanism prior to that. In Oligocene there were some lakes, some very special coal is also here, but almost microscopic amount. The main coal is here, and then there are shales, and they are so organic rich, these clays, that they were even thinking that they would be very good for some chemical industry, even source of energy. But that's away now, because they use it for remediation, reclamation of the land, to make it after coal. Yeah, this is the restoration, different pictures, what the country looked like when it was wood with some rivers and some only marginal lake. Then the lake was growing, and whether there were trees or whether it was open country without woods. Okay, they make 3 to 5 exploration boreholes per year. Sorry. They have hundreds of wells already, and this is how they make correlation. Masaryk University here, you have instrument hand X-ray fluorescence. You get chemical composition of whatever rocks or materials. He is using this and makes some geochemical correlation of the profiles, because he wants to know where he is and how deep is the predicted coal. He published several papers, excellent papers. So laboratory, this is cation exchange capacity, measured all some minerals, very nice. And here is a Krandalit. He found this mineral as a marker, as a stratigraphic marker, so that he can correlate different horizons. It is shown here. You see 1, 2, 3. These are Krandalit horizons in the overburden. So that is how a coal geologist works in a company. And this is what is the restoration of the evolution of the basin. So first it was a woody, wet forest, changing to a lake, and there was some river deposition, and then the final stage was that everything was covered by a big, big lake. Sorry. Sokolov is like an hour from Bílina, going southwest. Look how the scene is narrow when compared with Bílina. Lot of sandstones, gravels, and clays. Excavator. You can imagine that you would be big like this. So how big is the excavator? And it is taking the overburden here, and here it puts to train, and the train takes it away. In many places they are conveyors, that means pásy, dopravníky, not trains, but this is for the purpose of business, that they are selling it somewhere, so that's why they put it to a train. And these are the overburdened clays, and they are very laminated, and they are very organic rich and have fantastic chemical properties for even for water cleaning and so on. Absorption. Now let's move to Ostrava Karviná, and that is Upper Silesian Basin. So it is northeastern part, and this is the lithostratigraphy. What we need to remember only that this is Upper Carboniferous, and there is a lot of eroded stuff on top, so we see an erosional relic, not the youngest strata that were deposited. This is what it looks like. This is Ostrava Formation, and this is Karviná Formation. It goes to Poland, and in Poland it is 20 times bigger. And you will see how the production in Poland is much bigger than what we have. And by the way, these are coal bed methane test wells, these bluish things. In 2001, our government paid 1 billion crowns, that is 1,000 millions, translated to English, to explore coal bed methane. That in coal you have here and then methane gas, and how to make fracturing, hydraulic fracturing, and pump the gas and produce a lot of gas to get energy. So it was as if not very successful event, but we had a very nice 2 years of working on coal bed methane. So what is interesting, there are producing gas fields. All what's shown here are a green gas company is producing gas from these places. They are producing also from here, but I wanted to show the coal fields. And the last coal field, ČSM, used to be Československá mládež. So JSM is the last coal field that still is operating. Wednesday is the time when we go to visit it. What does bituminous coal look like in microscope? The only interesting thing, so in grayish vitrinite, that is homogeneous, you can find megaspores, very large spores, that means reproductive something from trees in that matter, and this is hydrogen rich, that means it makes more hydrocarbon. When you retort this coal and make coke, in nature, the coke is this. It's full of inertinite and it's charcoal. Dřevěné uhlí vzniká tak, že za nepřístupu vzduchu vystavíte vysokým teplotám uhlí. So charcoal is full of inertinite if it's made by man. If it's made by nature, it is inertinite coal, and you can see it with very bright white colors. This is again inertinite called fusinite. It's very sharp, and if you go to Žensko after the fires, and after 1 million years, there will be a sedimentary layer full of inertinite or fusinite. This is this type of. This is from natural forest fires. Not only forest, but also peat fires. And something between is semi-fusinite, and you see that in microscope you can distinguish many things, and you can say if it's good for coking, to znamená koksovatelné uhlí důležité pro železárny. By the way, třinecké železárny, steel factory, needs coking coal. And they were doing this from JSM mine and from the other closed down mine. Now they have to buy it from Australia. You will see within 5 years the price will go up like this. Nowadays, because we still produce, they do not sell us for high price, but they will immediately do when we close all mines. Now the final, so historical coal production, 1900, and here we are 2019, and you cannot read it, but this is United States, this is Europe, maybe Germany or France or Britain, the same, goes down, and India is going up, Russia is fluctuating. In fact, now I am confused who is USA and who is, this is Russia, so this is Russia, and USA is this much. But this is China. And that is, so what do they do with the coal? Do they burn it? If they burn it, if we close down these mines, shall we save the climate? If they still go and burn it, nobody will see whatever happens here. This will control the budget, complete result of the climate change. Of course, I'm not saying that they control the climate, but they contribute by CO2 this much, and it's still growing. And Czechia is 49 megatons. China is 3,600 or 700 megatons. So we can compare, whereas Poland is, you see, like something more than double what we used to produce. So this is the evolution in Poland. These are millions of metric tons per year. The total production, they go down, but this is Czechia. So, and this is exported Polish coal. And this is the basket. So energy in Poland is produced by this much from brown coal, bituminous coal, gas, biogas, wind, dark is water because they are flat land, and these are the others. So you see what is today and where is it going. And this is in Czech Republic. So this is brown, this is typical brown color. So brown coal production goes like this, and bituminous coal like this. And this is 1990, 1918, and today it's somewhere here. So that is the evolution, that is the history of production, and it is everywhere emphasized that coal will be shut down. And Poland plans to shut down in 2049, Czech Republic 2024, that is next year. So where do we go? So what are the possibilities? It is all about that there are certain limits, and if they are not broken, then next year it's finished with Ostrava or Karviná, and with brown coal it is just very, very next years. But still something goes on, and these are the modern power plants. You don't see any smoke anymore, and because the new technologies make the energy in a very different, in a different way, and this is so-called supercritical technology with steam temperature 600 degrees, not 100 but 600, and CO2 emissions by 20% lower than the previous plants. So it reduced, and soot and sulfur removed, of course. But now the trend is to find, can we store carbon dioxide from these plants, because there are technologies which can take CO2 from the emissions and bring them and store them into geological bodies. So if that is the way, Norwegians say, just give us all your CO2 and we will store it in North Sea, in the depleted oil and gas field. I think, thank you for your attention, and thank you Buriane, nice paintings of carbon in the forest wetlands.